Hello there, and welcome to a gentle journey through the invisible world that surrounds us every moment of every day. I'm so glad you found your way here tonight. Perhaps you've had one of those days where your mind won't quiet down, or maybe you're simply someone who finds peace in understanding the quiet mysteries that dance above our heads. Either way, this evening's exploration is crafted just for you. You have nothing to do right now except rest. Let your shoulders drop, your breathing slow, and your thoughts drift like clouds across a summer sky, because tonight we're going to wander through the atmosphere itself. That magnificent blanket of gases that wraps around our planet like a protective embrace. We'll discover gentle truths about the air currents that carry birds on their journeys, the delicate ice crystals that paint our winter mornings, and the invisible forces that create the weather patterns we experience every single day. From the softest morning mist to the grandest thunderclouds, from rainbow arcs that bridge the sky to snowflakes that fall like tiny works of art, we'll explore 100 peaceful facts about the weather that might just surprise you or spark some quiet curiosity as you drift towards sleep. And before we begin this atmospheric adventure, if these calm explorations help you unwind at the end of your day, consider subscribing to the channel. It helps others discover this peaceful corner of the internet, one sleepy soul at a time. Now, let's begin our gentle ascent into the world of weather. The atmosphere that surrounds our planet extends roughly 100 kilometers above our heads, but it's not uniform like a simple shell. Instead, it's layered like a delicate cake, each section with its own personality and purpose. The lowest layer, called the troposphere, is where virtually all weather happens. This is our weather kitchen, extending from the ground up to about 10 kilometers high, where temperature drops as you climb higher, creating the perfect conditions for clouds to form and storms to brew. Above the troposphere lies the stratosphere, a curious place where the rules seem to reverse themselves. Here, temperatures actually increase with altitude, warming as you travel higher due to the gentle absorption of the sun's ultraviolet rays by ozone molecules. It's in this quiet layer that those rare and beautiful mother-of-pearl clouds sometimes form, shimmering with colors that seem almost too delicate to be real. Weather, at its heart, is simply the atmosphere's way of trying to balance itself. Imagine the Earth as a giant sphere, receiving uneven heating from the sun. The equatorial regions bask in intense, direct sunlight throughout the year, while the polar regions receive only oblique rays and experience months of darkness during winter. This creates temperature differences that the atmosphere constantly works to smooth out, like water flowing from a high place to a low place, seeking equilibrium. These temperature differences create pressure variations across the globe. Warm air becomes less dense and rises like a hot air balloon, while cold air sinks like a stone through water. The Earth's rotation adds another gentle complexity through something called the Coriolis effect, which deflects moving air masses and creates those graceful spiral patterns we see in weather systems from space. This cosmic dance of air creates semi-permanent pressure systems that shift and breathe with the seasons. Around 30 degrees latitude, both north and south, subtropical high-pressure zones form like invisible mountains of dense air. Near 60 degrees latitude, subpolar low-pressure areas develop like atmospheric valleys, where storms tend to gather and intensify. High above our heads, between 9 and 16 kilometers up, flow the jet streams, those remarkable rivers of air that race around the planet at speeds that can exceed 400 kilometers per hour. These high-altitude currents act like highways for weather systems, steering storms across continents and influencing temperature patterns far below. When jet streams meander in lazy waves, they can cause weather patterns to persist for days or weeks, creating those memorable heat waves or extended cold spells that we remember years later. The jet streams follow the boundaries between hot and cold air masses, weaving north and south like a ribbon in the wind. Sometimes they speed up, sometimes they slow down, and occasionally they break apart entirely, creating what meteorologists call blocking patterns that can redirect storms in unexpected ways. Within our atmosphere, moisture plays the role of a master artist, painting the sky with an endless variety of cloud formations. Water exists in 3 states in our atmosphere, constantly transforming from invisible vapor to liquid droplets, to ice crystals and back again. This eternal dance of phase changes is what creates the spectacular displays we see overhead. Clouds form when air becomes saturated with water vapor and can no longer hold it all in invisible form. This usually happens when air is cooled, either by rising to higher altitudes where temperatures are lower, or by coming into contact with a cooler surface. As water vapor condenses, it needs something to condense onto, tiny particles called condensation nuclei. These can be specks of dust, pollen, salt from ocean spray, or even microscopic particles from volcanic eruptions half a world away. The atmosphere contains an estimated 16 million thunderstorms each year, with roughly 2,000 in progress at any given moment. These magnificent atmospheric engines represent some of nature's most impressive displays of power, capable of releasing energy equivalent to several nuclear bombs. Yet they begin with something as simple as warm, moist air, encountering cooler air aloft, creating instability that allows air masses to rise rapidly through the atmosphere. As these air masses ascend, they cool and condense, releasing latent heat that further fuels the storm's growth. The process creates towering cumulonimbus clouds that can reach heights of 60,000 feet or more, with their distinctive anvil-shaped tops spreading out like umbrellas when they encounter the boundary between the troposphere and stratosphere. Lightning represents one of nature's most dramatic displays, involving a near instantaneous release of energy that briefly heats the air to temperatures of about 50,000 degrees Fahrenheit, making the lightning channel 5 times hotter than the surface of the sun. This extreme heating causes the air to expand so rapidly that it creates a shockwave traveling at supersonic speeds. Thunder is this shockwave transforming into sound as it slows down and spreads through the atmosphere. The delay between seeing lightning and hearing thunder occurs because light travels at approximately 300 million meters per second, while sound travels at only 343 meters per second through air. By counting the seconds between lightning and thunder and dividing by 5, you can estimate your distance from the lightning strike in miles. Precipitation begins its journey high in the atmosphere, where water droplets or ice crystals form within clouds. Sometimes this precipitation evaporates completely before reaching the ground, creating ghostly streaks called virga that hang from cloud bases like nature's own curtains. These ethereal formations are particularly common in arid regions where the air near the ground is extremely dry. When conditions are perfect for snow formation, the process is surprisingly intricate. A snowflake begins when an extremely cold water droplet freezes onto a tiny particle of pollen or dust high in the sky, creating an ice crystal nucleus. As this crystal falls toward Earth, water vapor freezes directly onto it through a process called deposition, building the 6 arms of the snowflake in perfect symmetry. The hexagonal shape of snowflakes reflects the molecular structure of ice itself, where water molecules arrange themselves in predetermined patterns. Although the 6-sided shape is always maintained, each snowflake's intricate details are determined by the atmospheric conditions it encounters during its fall. A crystal might begin growing in one pattern, then shift to another as it encounters different temperatures or humidity levels. Because all 6 arms experience the same conditions simultaneously, they develop identically, creating those perfect symmetrical patterns that have fascinated humans for centuries. In extremely cold conditions, when temperatures drop below -30 degrees Celsius, something magical called diamond dust can form. These are microscopic ice crystals so small and light that they remain suspended in the atmosphere, creating an otherworldly shimmer that truly resembles floating diamonds. When illuminated by sunlight or artificial lights, these crystals create stunning optical effects, including light pillars that appear to extend upward from light sources, like ethereal columns reaching toward the heavens. Sometimes weather creates phenomena so rare and beautiful that they seem almost mythical. Heat bursts represent one such mystery, occurring when temperatures can spike by 20 to 30 degrees Fahrenheit within minutes, accompanied by fierce winds exceeding 80 miles per hour. These extraordinary events happen when dying thunderstorms create columns of cooling air that descend rapidly through the atmosphere, becoming superheated through compression as they fall. The formation of rainbows requires precise conditions that transform ordinary sunlight into arcs of pure color. When sunlight encounters millions of water droplets suspended in the air, each droplet acts as a tiny prism, dispersing white light into its component colors. The primary rainbow displays colors in a specific order from outside to inside: red, orange, yellow, green, blue, indigo, and violet. The angle at which rainbows appear is always 42 degrees from the anti-solar point, the point directly opposite the sun from the observer's perspective. Sometimes nature creates even more spectacular displays. When semi-transparent cirrus clouds contain precisely aligned ice crystals and the sun reaches at least 58 degrees above the horizon, circumhorizontal arcs can form. These fire rainbows appear as horizontal bands of color that seem to set the clouds ablaze with prismatic light, creating the illusion that the sky itself is burning with rainbow fire. In polar regions during the depths of winter, when stratospheric temperatures plummet below -80 degrees Celsius, rainbow clouds can form at altitudes between 15 and 25 kilometers. These nacreous clouds, also called mother-of-pearl clouds, create some of the most spectacular light shows on Earth. The ice crystals that form these clouds are incredibly thin and delicate, only a few micrometers in diameter, which allows them to diffract sunlight into brilliant shifting colors. Along coastlines around the world, marine layers create some of the most persistent and influential weather patterns. These form when warm air moves over cooler ocean surfaces, creating stable layers of cool, moist air near the water, topped by warmer, drier air above. The temperature inversion acts like an atmospheric lid, trapping cool, humid air and creating ideal conditions for low-lying stratus clouds and fog that can persist for days. In Southern California, this phenomenon creates the famous June gloom, where overcast skies and cool temperatures persist through late spring and early summer. The marine layer follows a predictable daily cycle, thickening overnight as temperatures drop and often dissipating by mid-morning as inland areas heat up and create onshore flow patterns. Trade winds, named for their favorable influence on trading ships crossing subtropical oceans, represent one of the most consistent wind patterns on Earth. These winds flow westward and toward the equator on the equatorward side of subtropical high-pressure centers, creating the steady breezes that have guided sailors across oceans for thousands of years. The atmosphere's ability to create optical illusions rivals any magician's tricks. Light pillars form when plate-shaped ice crystals in the atmosphere reflect light sources, creating vertical columns of light that appear to extend upward from street lamps, the sun, or moon. These ethereal displays are most common during very cold weather, when ice crystals naturally orient themselves horizontally as they drift through the air. Weather operates on scales ranging from the microscopic to the planetary. Individual water molecules dance through phase changes in processes too small to see, while massive atmospheric circulation patterns span entire continents. The trade winds that blow across tropical oceans merge near the equator in a zone called the intertropical convergence zone, where they rise and flow eastward at altitudes of 2 to 17 kilometers, creating a circulation pattern that helps regulate Earth's climate. Sometimes the atmosphere creates phenomena that seem to defy explanation, like the mysterious morning glory clouds that roll across northern Australia like enormous invisible waves made visible. These rare formations can stretch for hundreds of kilometers, appearing as perfectly cylindrical clouds that move steadily across the landscape at speeds of up to 60 kilometers per hour. They form when specific atmospheric conditions create a rotating horizontal vortex. with air rising on one side of the cloud and descending on the other, creating a rolling motion that can persist for hours. The atmosphere holds secrets in its temperature patterns that reveal themselves only to careful observation. Temperature inversions occur when warm air sits atop cooler air, reversing the normal pattern where temperature decreases with altitude. These atmospheric puzzles can trap pollutants close to the ground, creating those hazy layers you sometimes see hugging valleys and cities. But they also create ideal conditions for some of nature's most beautiful displays, allowing sounds to carry much farther than usual and creating those crisp, clear mornings when distant mountains seem close enough to touch. In the delicate dance of atmospheric pressure, even tiny changes can have profound effects. A drop of just a few millibars can signal the approach of a storm system days before clouds appear on the horizon. Animals seem particularly sensitive to these pressure changes, with many species altering their behavior in response to atmospheric shifts too subtle for humans to detect without instruments. The wind carries stories from thousands of kilometers away, transporting dust from African deserts across the Atlantic Ocean to fertilize Amazon rainforests, or carrying volcanic ash around the globe to paint spectacular sunsets in places far from any volcano. These invisible rivers of air move an estimated 1 billion tons of dust around our planet each year, connecting distant ecosystems in ways that scientists are only beginning to understand. Atmospheric rivers represent some of the most important moisture transport mechanisms on Earth, carrying water vapor in narrow bands that can be thousands of kilometers long and hundreds of kilometers wide. When these rivers in the sky encounter mountain ranges, they can dump enormous amounts of precipitation, sometimes delivering more water in a few days than the region typically receives in months. Despite their immense power, these atmospheric rivers are often invisible to the naked eye, revealing themselves only through satellite imagery and their effects on the landscape below. The boundary layer, that lowest portion of the atmosphere where we live and breathe, has its own unique characteristics that change throughout the day. During daylight hours, solar heating creates turbulence that mixes the air. But at night, this layer becomes stable and stratified, allowing temperatures to drop more rapidly and creating those calm, still conditions perfect for morning frost formation. Fog forms through several different mechanisms, each creating its own distinctive patterns and behaviors. Radiation fog develops on clear, calm nights when the ground cools rapidly, chilling the air above it until water vapor condenses into countless tiny droplets suspended just above the surface. This type of fog typically forms in valleys and low-lying areas where cold air naturally collects, creating those ethereal blankets of white that seem to flow like slow rivers through the landscape. Advection fog occurs when warm, moist air moves over a cooler surface, gradually cooling until it reaches its saturation point. This type of fog is common along coastlines, where warm air from over land encounters cooler ocean waters, creating those mysterious walls of white that can suddenly engulf entire cities in a matter of minutes. The atmosphere's ability to bend and scatter light creates an endless variety of optical phenomena. Sundogs, those bright spots of light that sometimes appear on either side of the sun, form when sunlight passes through hexagonal ice crystals in cirrus clouds. These crystals act like prisms, refracting light at specific angles to create these colorful companions to the sun that seem to follow it across the sky. Halos around the sun or moon form through similar processes, created when light passes through ice crystals in thin, high clouds. The most common halo appears as a circle with a radius of 22 degrees around the light source. But more complex displays can create multiple rings, arcs, and bright spots that transform the sky into a celestial light show. Green flashes represent one of the most elusive atmospheric optical phenomena, visible for just a second or two as the sun disappears below a clear horizon. This brief emerald spark occurs because Earth's atmosphere acts like a weak prism, separating sunlight into its component colors. Red light, being bent least by the atmosphere, disappears first, followed by orange, yellow, and blue. Green light, being bent more than red, but less than blue, becomes the last visible color in that final moment before the sun vanishes completely. The atmosphere creates its own music through the interaction of wind with various surfaces and obstacles. When wind flows over mountains, it can create standing waves that extend high into the atmosphere, sometimes reaching altitudes where commercial aircraft cruise. These mountain waves can produce some of the strongest turbulence experienced by pilots. Yet they remain completely invisible, except for the occasional lenticular clouds that form in their crests. Microbursts represent concentrated columns of sinking air that can create devastating winds when they reach the ground and spread outward in all directions. Despite their small size, typically less than 4 kilometers in diameter, these atmospheric phenomena can produce winds exceeding 160 kilometers per hour, creating conditions more dangerous than many tornadoes. The global wind patterns that girdle our planet create a complex three-dimensional circulation system that helps regulate Earth's temperature. The Hadley cells, massive convection loops that extend from the equator to about 30 degrees latitude, transport enormous amounts of heat from tropical regions toward the poles. These circulation patterns create the trade winds that blow consistently across tropical oceans, the horse latitudes where sailing ships once became becalmed, and the westerly winds that dominate middle latitudes. Between these major circulation patterns lie transition zones where air masses of different temperatures and humidity levels meet and interact. These frontal boundaries can extend for thousands of kilometers, creating the elongated bands of clouds and precipitation that appear on satellite images like brushstrokes across the planet's canvas. Temperature gradients in the atmosphere can be surprisingly sharp, with differences of several degrees occurring over distances of just a few meters. These microscale variations create their own circulation patterns, generating the thermal updrafts that birds use to soar effortlessly for hours without flapping their wings, and the downdrafts that can suddenly rob aircraft of lift. The atmosphere's capacity to store and transport water is truly remarkable. A single cubic meter of saturated air at tropical temperatures can hold almost 40 grams of water vapor, while the same volume of air at freezing temperatures can hold barely 5 grams. This dramatic difference in moisture holding capacity drives much of the world's weather, as air masses cool and release their excess moisture in the form of clouds and precipitation. Atmospheric pressure waves travel through the air like ripples on a pond, carrying information about distant weather events. These pressure oscillations, too subtle for humans to feel, can circle the globe multiple times, creating faint echoes of major storms and volcanic eruptions that sensitive instruments can detect thousands of kilometers away from their source. The diurnal cycle of heating and cooling creates predictable patterns in atmospheric behavior that vary with the seasons and geographic location. In many regions, winds follow daily patterns, strengthening during afternoon hours when solar heating creates maximum instability, then calming during the night as the atmosphere stabilizes under radiational cooling. Cloud streets form when cold air moves over warmer surfaces, creating parallel rows of cumulus clouds that can extend for hundreds of kilometers. These atmospheric highways form when convection organizes itself into regular patterns, with rising air creating clouds along predictable lines, while sinking air between the streets keeps those areas clear. The atmosphere's electrical activity extends far beyond the lightning we can see. A global electrical circuit constantly operates between the Earth's surface and the ionosphere, with thunderstorms acting like batteries that maintain a voltage difference of several 100,000 volts between the ground and the upper atmosphere. St. Elmo's fire appears as a bluish or violet glow around pointed objects during thunderstorms, created when the atmosphere's electrical field becomes so intense that it ionizes air molecules near sharp edges. This phenomenon has fascinated sailors for centuries, appearing on ship masts and rigging during storms like ghostly flames that burn without heat. Ball lightning remains one of the atmosphere's most mysterious phenomena. appearing as glowing spheres that can persist for several seconds during thunderstorms. These rare electrical displays can move slowly through the air, pass through solid objects, and disappear with loud pops, or simply fade away silently, leaving scientists with more questions than answers about their true nature. Atmospheric tides, caused by the sun's heating of the atmosphere, create subtle but measurable variations in pressure that occur twice daily. These atmospheric rhythms are most pronounced in tropical regions, where the regular heating and cooling cycle creates pressure waves that circle the globe with clock-like precision. The boundary between different air masses can be remarkably sharp, creating invisible walls in the atmosphere where temperature, humidity, and wind direction change dramatically over distances of just a few hundred meters. These atmospheric boundaries can persist for days, creating long-lasting weather patterns that affect millions of people across vast geographic regions. Kelvin-Helmholtz waves form when layers of air move at different speeds, creating the atmospheric equivalent of ocean waves. These undulations in the sky sometimes become visible when moisture condenses along the wave crests, creating clouds that look like breaking ocean waves frozen in mid-air. The atmosphere's memory extends much longer than most people realize, with circulation patterns and temperature anomalies persisting for weeks or months through complex feedback mechanisms. El Niño and La Niña events demonstrate this atmospheric persistence, creating weather patterns that can influence global climate for years at a time. Polar stratospheric clouds require some of the most extreme conditions on Earth to form, appearing only when stratospheric temperatures drop below -80 degrees Celsius. These ethereal formations create some of nature's most spectacular light shows, visible primarily during polar twilight, when the sun illuminates these high-altitude clouds from below while the lower atmosphere remains in darkness. Clear air turbulence occurs in seemingly calm skies, created by wind shear along the boundaries of jet streams or mountain waves. This invisible phenomenon can create sudden, severe jolting that affects aircraft flying through apparently clear air, demonstrating that the atmosphere holds surprises even when it appears perfectly tranquil. The nocturnal boundary layer develops each evening as the ground cools and the lowest portion of the atmosphere becomes stable and stratified. This nightly transformation allows temperatures to drop more rapidly, sounds to carry farther, and creates ideal conditions for dew and frost formation as moisture condenses on surfaces cooled by radiational heat loss to space. Atmospheric gravity waves ripple through the air like invisible tsunamis, created when air is displaced vertically and then oscillates up and down under the restoring force of gravity. These waves can travel for thousands of kilometers through the atmosphere, carrying energy from their source regions to distant locations where they can trigger cloud formation or clear existing clouds through their gentle vertical motions. The morning calm that settles over lakes and valleys represents one of the atmosphere's most peaceful phenomena. As the sun rises and begins heating the Earth's surface, thermal differences create the first gentle stirrings of convection. Dewdrops form during these quiet hours, when surfaces cool below the dew point, creating those perfect spheres of water that jewel spiderwebs and grass blades with crystalline beauty. Frost forms through a process called sublimation, where water vapor transforms directly into ice crystals without first becoming liquid. This delicate process requires clear skies, calm winds, and temperatures that drop below freezing. The intricate patterns that frost creates on windows and leaves are determined by tiny imperfections and nucleation sites that guide crystal growth into those familiar feathery designs. Valley breezes develop during daylight hours as mountain slopes heat faster than valley floors, creating upslope winds that carry moisture and sometimes cumulus clouds up mountainsides. At night, the pattern reverses as mountain slopes cool rapidly through radiation, creating downslope winds that drain cold air into valleys like invisible waterfalls. Sea breezes form along coastlines when land heats faster than adjacent water bodies during the day. The rising warm air over land creates a pressure difference that draws cooler air inland from over the water. This daily circulation can penetrate dozens of kilometers inland, bringing relief from heat and sometimes triggering afternoon thunderstorms where the sea breeze converges with existing weather patterns. Temperature inversions create fascinating acoustic phenomena, allowing sounds to travel much farther than normal by bending sound waves back toward the ground instead of letting them escape into the upper atmosphere. On inversion mornings, voices can carry across valleys with startling clarity, and distant train horns seem to echo from impossibly far away. Mammatus clouds create one of nature's most unusual displays, appearing as pouch-like protrusions hanging from the underside of cumulonimbus clouds. These rare formations develop when cold, dense air sinks through warmer air below, creating bulbous shapes that look like atmospheric udders suspended in the sky. They typically form after severe thunderstorms and can persist for several hours. Roll clouds appear as horizontal tubes that seem to slowly rotate about their axis as they move across the landscape. These rare formations develop along convergence zones where different air masses meet, creating a circulation that becomes visible when moisture condenses along the rotating cylinder of air. The most famous roll clouds occur in northern Australia, where they can stretch for hundreds of kilometers. Shelf clouds form along the leading edge of thunderstorms, appearing as dark horizontal wedges that seem to race across the sky. These ominous formations develop where cold downdrafts from storms spread outward at ground level, lifting warm, moist air ahead of the storm. The dramatic appearance of shelf clouds often signals the approach of strong winds and heavy rain. Lenticular clouds form when stable air flows over mountains, creating standing waves in the atmosphere. These smooth, lens-shaped clouds appear to hover motionless near mountain peaks, though they're actually constantly forming on the upwind side and dissipating on the downwind side as air moves through the wave pattern. Pilots know these clouds mark areas of severe turbulence and typically avoid flying near them. Asperitas clouds represent one of the newest officially recognized cloud types, appearing as dramatic undulations that seem to roll across the sky like ocean waves viewed from below. These rare formations create an otherworldly appearance that can make observers feel as though they're looking up at the seafloor from beneath turbulent waters. Fall streak holes, sometimes called hole punch clouds, appear as large circular or elliptical gaps in thin cloud layers. These formations develop when aircraft pass through supercooled water droplet clouds, triggering rapid ice crystal formation that spreads outward in expanding circles. The process can create spectacular displays, where rainbow colours appear around the edges of these atmospheric windows. Noctilucent clouds form at the very edge of space, approximately 80 kilometers above Earth's surface in the mesosphere. These ethereal formations are visible only during summer months at high latitudes, appearing as electric blue wisps against the darkening sky after sunset. They consist of ice crystals that form around meteoric dust particles in the extremely thin air of the upper atmosphere. Banner clouds form on the lee side of mountain peaks, when wind flows over sharp ridges and creates localized areas of reduced pressure. These clouds appear to stream from mountaintops like flags in the wind, constantly forming and dissipating as air flows through the low pressure zone. The Matterhorn's banner cloud is perhaps the most famous example of this phenomenon. Pyrocumulus clouds develop above intense heat sources like wildfires or volcanic eruptions, created when extreme surface heating causes air to rise rapidly and form towering cumulus formations. These fire clouds can grow into full thunderstorms, sometimes producing lightning that can ignite additional fires, creating a dangerous feedback loop between fire and weather. Wall clouds appear as localized lowerings in the base of supercell thunderstorms, marking areas where powerful updrafts are drawing air upward with tremendous force. These rotating formations often precede tornado development and represent some of the most dramatic cloud formations associated with severe weather. The wall cloud's slow rotation can be mesmerizing to watch, though it signals potentially dangerous conditions. Supercells represent the atmosphere's most organized and persistent thunderstorm type, featuring rotating updrafts called mesocyclones that can persist for several hours. These storms move slowly across the landscape, often deviating from the general wind flow as their internal circulation interacts with environmental winds. They're responsible for producing the most damaging tornadoes, largest hail, and most destructive winds. Derechos create widespread wind damage across linear paths that can extend for hundreds of kilometers. These organized systems of thunderstorms produce sustained winds exceeding 100 kilometers per hour, creating swaths of destruction that rival those of tornadoes, but cover much larger areas. The name comes from the Spanish word for straight, referring to the linear nature of the damage pattern. Squall lines form when multiple thunderstorms organize into long, narrow bands that can stretch for hundreds of kilometers. These systems often develop along cold fronts, creating impressive walls of storms that march across the landscape with remarkable organization. The leading edge of a squall line typically produces the most severe weather, including damaging winds, hail, and occasionally tornadoes. Bow echoes appear on weather radar as curved lines of storms that resemble archers' bows. These formations develop when strong downdrafts in the center of a squall line create areas of particularly damaging winds called downbursts. The curved appearance results from the storms on either end of the line moving faster than the center, creating the characteristic bow shape. Mesoscale convective complexes represent some of the largest organized thunderstorm systems, covering areas comparable to entire states and persisting for 12 hours or more. These massive systems typically develop during summer evenings and can produce significant rainfall over large regions, sometimes causing widespread flooding, while also providing beneficial moisture to agricultural areas. Atmospheric rivers transport water vapor in narrow bands that can carry moisture equivalent to 15 times the flow of the Colorado River. When these rivers in the sky encounter mountainous terrain, they can produce extreme precipitation events that fill reservoirs and cause flooding simultaneously. The phenomenon demonstrates the atmosphere's remarkable capacity to transport water across vast distances. Orographic lifting occurs when air masses encounter mountain ranges and are forced to rise, cooling and condensing their moisture content on the windward slopes. This process creates distinct climate patterns with wet conditions on one side of mountains and dry conditions on the lee side, known as rain shadows. The effect can be so pronounced that ecosystems change dramatically over short distances. Chinook winds develop when air flows over mountain ranges and descends on the lee side, warming and drying as it compresses. These foehn winds can raise temperatures by 20 degrees Celsius or more in just a few hours, rapidly melting snow and creating dramatic weather changes that affect everything from aviation to agriculture. Katabatic winds form when cold air drains downward along slopes under the influence of gravity. These drainage winds are most pronounced in mountainous regions and polar areas, where they can reach hurricane-force speeds as dense, cold air accelerates down steep terrain. Antarctica experiences some of the world's strongest katabatic winds, with speeds regularly exceeding 200 kilometers per hour. Gap winds develop when air is funneled through mountain passes or valleys, accelerating as it squeezes through the narrow opening. These channeled winds can create localized areas of extreme wind speeds that persist even when surrounding areas remain calm. The Columbia River Gorge is famous for its gap winds that create world-class windsurfing conditions. Dust devils form when intense surface heating creates rotating columns of air that become visible by lifting dust and debris. These miniature tornadoes are most common in arid regions during hot afternoons, typically lasting only a few minutes, but occasionally reaching heights of several hundred meters. Unlike tornadoes, dust devils form from the ground up in clear weather conditions. Haboobs create walls of dust that can tower thousands of meters high and extend for hundreds of kilometers. These dramatic dust storms form along the leading edge of thunderstorm downdrafts, where powerful winds lift enormous quantities of dust and sand, into towering walls that advance across the landscape like brown tsunamis. Sandstorms transport millions of tons of dust across continents and oceans, carrying nutrients from one ecosystem to another and influencing weather patterns thousands of kilometers from their source. The Sahara Desert regularly sends dust across the Atlantic Ocean to the Amazon basin, providing essential minerals that help sustain rainforest growth. Atmospheric blocking patterns occur when high-pressure systems become stationary and redirect the normal flow of weather systems around them. These blocks can persist for weeks, creating prolonged periods of unusual weather such as heat waves, droughts, or extended cold spells. The phenomenon demonstrates how relatively small changes in atmospheric circulation can have far-reaching consequences. Rossby waves are planetary-scale atmospheric waves that meander around the globe, created by the interaction between the Earth's rotation and atmospheric flow patterns. These massive undulations in the jet stream can influence weather patterns across entire continents, creating the large-scale patterns that determine whether regions experience warm or cool, wet or dry conditions. The polar vortex represents a large-scale circulation pattern that normally keeps Arctic air confined to polar regions. When this vortex weakens or becomes distorted, it can allow frigid air to spill southward into lower latitudes, creating sudden and severe cold outbreaks that can bring Arctic conditions to regions accustomed to much milder weather. Sudden stratospheric warming events occur when the polar vortex in the stratosphere rapidly weakens or even reverses direction, causing temperatures in the Arctic stratosphere to rise by 50 degrees Celsius or more in just a few days. These dramatic events can influence surface weather patterns for weeks or months, often leading to prolonged cold periods in mid-latitude regions. Teleconnections link weather patterns across vast distances through atmospheric and oceanic circulation patterns. El Niño events in the tropical Pacific can influence weather from Australia to North America, demonstrating how the atmosphere connects distant regions through complex feedback mechanisms that scientists are still working to understand fully. The Madden-Julian oscillation represents a traveling pattern of enhanced and suppressed tropical rainfall that circles the globe every 30 to 60 days. This atmospheric rhythm influences monsoon patterns, hurricane activity, and weather conditions across tropical and subtropical regions, showing how the atmosphere operates on timescales much longer than individual weather events. Quasi-biennial oscillation describes a cyclical pattern in stratospheric winds above the equator that reverses direction approximately every 26 months. This high-altitude rhythm influences weather patterns around the world, affecting everything from hurricane seasons to winter weather in the Northern Hemisphere through complex atmospheric connections. Arctic oscillation and North Atlantic oscillation represent seesaw patterns in atmospheric pressure that influence weather across large regions. When these oscillations are in their positive phases, they tend to keep cold Arctic air locked in polar regions, while negative phases allow cold air to spill southward, affecting weather patterns across entire continents. Atmospheric momentum transport moves energy and rotation around the globe through complex interactions between winds at different altitudes. This invisible process helps explain why the atmosphere doesn't simply settle into a static pattern, but instead maintains the dynamic circulation systems that create our ever-changing weather. Baroclinic instability drives the formation of mid-latitude cyclones, those spiraling storm systems that bring much of the weather to temperate regions. This instability develops along boundaries between air masses of different temperatures, converting the potential energy stored in temperature gradients into the kinetic energy of rotating storm systems. Potential vorticity represents a measure of the atmosphere's rotation tendency that remains conserved as air parcels move through the atmosphere. This invisible property helps meteorologists track and predict the movement of weather systems, providing insights into how atmospheric disturbances will evolve and move across the landscape. The atmosphere's three-dimensional structure creates multiple levels where different processes operate simultaneously. While surface weather systems move according to low-level wind patterns, upper-level disturbances can steer these systems or trigger new development through complex vertical interactions that extend throughout the troposphere. Synoptic scale weather systems span hundreds to thousands of kilometers and persist for days to weeks, representing the scale of weather patterns most familiar to daily experience. These systems include the high and low pressure areas shown on weather maps, cold and warm fronts, and the storm systems that bring changing weather conditions to most populated regions. Mesoscale phenomena operate on intermediate scales between synoptic systems and individual thunderstorms, including sea breeze circulations, mountain valley winds, and organized thunderstorm systems. These moderately sized weather features can significantly influence local weather conditions and often serve as the trigger mechanisms for more dramatic weather events. Microscale processes operate on the smallest scales of atmospheric motion, from individual turbulent eddies to the air circulation around buildings and trees. Though small in scale, these processes are crucial for understanding how heat, moisture, and pollutants are mixed through the atmosphere and how surface conditions influence weather development. The atmosphere's ability to create optical wonders extends far beyond simple rainbows and lightning displays. Crepuscular rays, often called God rays, form when sunlight streams through gaps in clouds, creating those dramatic beams of light that seem to radiate from the heavens themselves. These ethereal columns appear to diverge from their source, but this is simply a perspective effect, much like how parallel railroad tracks seem to converge in the distance. Anti-crepuscular rays create an even more mysterious display, appearing as bands of light that seem to converge toward the anti-solar point, the spot in the sky directly opposite the sun from your perspective. These rays are actually the continuation of crepuscular rays, extending across the entire sky in parallel lines that only appear to meet due to the curvature of our visual perspective. The atmosphere sometimes creates displays so unusual they seem borrowed from another world entirely. Sprites, elves, and blue jets represent forms of lightning that occur high above thunderstorms, reaching into the mesosphere and lower thermosphere. These upper atmospheric electrical phenomena were unknown to science until the 1990s, when pilots began reporting mysterious flashes of red and blue light dancing above storm clouds. Sprites appear as brief red flashes that can extend from 50 to 90 kilometers above the ground, lasting only a few milliseconds but covering enormous areas. They're triggered by powerful positive lightning strikes in the thunderstorm below, creating electrical discharges that illuminate the thin air of the upper atmosphere in ghostly red hues. Temperature patterns in the atmosphere create invisible boundaries that can be surprisingly persistent. Thermal belts form along hillsides, where cold air drainage creates zones of warmer temperatures at specific elevations. These narrow bands of favorable conditions can make the difference between frost damage and healthy crops, creating microclimates that experienced farmers learn to identify and utilize. Advection temperature patterns occur when air masses carry their thermal characteristics across vast distances. Warm air from subtropical regions can maintain its temperature as it travels poleward, while Arctic air masses can bring their frigid temperatures far into temperate zones. These traveling temperature patterns create the dramatic weather contrasts that make headlines when unusual warmth or cold arrives unexpectedly. The diurnal temperature range varies dramatically depending on atmospheric conditions and geographic location. Clear, dry air allows temperatures to swing widely between day and night, while cloudy, humid conditions moderate these swings by trapping heat near the surface. Desert regions can experience temperature ranges of 30 degrees Celsius or more between day and night, while coastal areas might see variations of only a few degrees. Urban heat islands demonstrate how human activities can modify atmospheric behavior on local scales. Cities typically remain several degrees warmer than surrounding rural areas, especially at night, due to the thermal mass of buildings and pavement, reduced vegetation, and heat generated by human activities. This warming effect can extend the growing season, reduce heating costs, but also increase cooling demands and affect local precipitation patterns. Atmospheric moisture exists in forms that extend far beyond the visible water droplets we see as clouds and fog. Supersaturation can occur when air contains more water vapor than it can normally hold, creating unstable conditions where the slightest disturbance can trigger rapid condensation. These supersaturated conditions often exist in the upper atmosphere, where water droplets can remain liquid at temperatures well below freezing. Sublimation represents one of the atmosphere's most elegant phase transitions, where ice transforms directly into water vapor without first melting into liquid. This process occurs constantly in winter conditions, gradually reducing snow and ice accumulations even when temperatures remain below freezing. The energy required for sublimation comes from solar radiation or ambient heat, creating the gentle disappearance of snow on sunny winter days. Hygroscopic nuclei demonstrate how microscopic particles can have enormous influences on atmospheric processes. These tiny particles, often salt crystals from ocean spray, attract water molecules so effectively that they can trigger condensation even before the air becomes fully saturated. Different types of nuclei require different humidity levels to activate, creating a complex hierarchy of condensation triggers throughout the atmosphere. Atmospheric electricity extends far beyond the lightning bolts we can see during thunderstorms. Point discharge occurs when electrical fields become so intense that electrons begin streaming from sharp objects, creating the faint crackling sounds sometimes heard around metal objects during storms. This process helps dissipate electrical charges before they can build to lightning levels. The global electrical circuit maintains a constant voltage difference between Earth's surface and the ionosphere, with fair weather areas acting as return current paths for the electrical energy generated by thunderstorms worldwide. This invisible electrical system operates continuously, carrying currents of about 1,000 amperes around the entire planet. Atmospheric chemistry involves countless reactions occurring simultaneously at different altitudes and under varying conditions. Ozone formation and destruction represent some of the most critical atmospheric chemical processes, with ozone serving as both a protective shield in the stratosphere and a harmful pollutant at ground level. The same molecule can be essential for life when it exists at high altitudes, but dangerous to breathe when found near the surface. Photochemical processes driven by solar radiation create and destroy atmospheric compounds throughout the day. These light-driven reactions are most intense during midday hours when solar radiation peaks, but they continue at reduced rates even during dawn and dusk, when specific wavelengths of light can still trigger molecular changes. Atmospheric layering creates distinct chemical environments at different altitudes. The boundary layer near Earth's surface contains the highest concentrations of water vapor and pollutants, while the free troposphere above maintains more uniform chemical composition. The tropopause acts as a barrier that prevents most surface-generated compounds from reaching the stratosphere, where they could have global effects. Condensation nuclei come in an astonishing variety of forms, each with different abilities to trigger cloud droplet formation. Sea salt particles excel at attracting water molecules, while dust particles provide surfaces for ice crystal formation. Biological particles from pollen, spores, and bacteria can also serve as nuclei, creating a living component in atmospheric water cycle processes. Cloud condensation nuclei concentrations can vary by orders of magnitude between pristine marine environments and polluted urban areas. Clean, oceanic air might contain only a few hundred particles per cubic centimetre, while heavily polluted air can contain hundreds of thousands. These variations dramatically affect cloud properties, with higher concentrations typically producing clouds with smaller droplets and different optical properties. The atmosphere's memory operates through various mechanisms that allow past conditions to influence future weather patterns. Soil moisture provides one form of atmospheric memory, as dry soils tend to promote continued dry conditions while wet soils help maintain humid atmospheric conditions. This feedback can persist for weeks or months, creating self-reinforcing weather patterns. Snow cover represents another form of atmospheric memory, reflecting incoming solar radiation and maintaining cold surface temperatures that can influence weather patterns for extended periods. The high albedo of snow-covered surfaces can keep regions cooler than they would otherwise be, affecting everything from local precipitation patterns to the timing of seasonal transitions. Oceanic thermal inertia provides the atmosphere with its longest-term memory, as the enormous heat capacity of water bodies allows them to moderate temperature changes over seasonal and even multi-year timescales. The ocean's ability to store and slowly release heat helps explain why coastal regions experience more moderate climates than continental interiors. Boundary layer development follows predictable daily cycles that vary with season, weather conditions, and surface characteristics. During stable nighttime conditions, the boundary layer can shrink to just a few dozen meters thick, creating a shallow layer where pollutants become concentrated and sounds travel with unusual clarity. Convective boundary layers develop during daytime heating, growing to heights of several kilometers as thermal updrafts mix air throughout the lower atmosphere. These well-mixed layers allow pollutants to disperse vertically, improve air quality, and create the turbulent conditions that produce those puffy cumulus clouds on fair weather days. Entrainment processes occur at the top of the boundary layer, where turbulent mixing gradually incorporates air from the free atmosphere above. This process can dramatically change boundary layer properties as dry air from aloft mixes with moist surface air, or as stable air from above dampens convective activity below. Atmospheric waves propagate through the air like ripples on a pond, carrying energy across vast distances without transporting the air itself. These waves can be generated by mountains, thunderstorms, or even distant earthquakes, creating disturbances that travel through the atmosphere at the speed of sound or faster. Internal gravity waves represent atmospheric oscillations that occur when stable air is displaced vertically and then oscillates up and down under the restoring force of buoyancy. These waves can propagate horizontally for thousands of kilometers, carrying energy from their source regions to distant locations where they can trigger cloud formation or dissipation. Atmospheric tidal effects, though subtle, create measurable variations in pressure that occur with the same regularity as ocean tides. These atmospheric rhythms are most pronounced in tropical regions, where the daily heating cycle creates pressure waves that circle the globe with remarkable consistency. Pressure wave propagation allows atmospheric disturbances to communicate across vast distances at speeds approaching that of sound. Major volcanic eruptions create pressure waves that can be detected multiple times as they circle the globe, demonstrating the atmosphere's ability to transmit information about distant events. Temperature oscillations in the atmosphere operate on timescales ranging from minutes to decades. Daily temperature cycles are the most familiar, but the atmosphere also exhibits weekly, monthly, seasonal, annual, and even multi-decadal temperature rhythms that influence everything from agriculture to energy consumption. Radiative processes control the atmosphere's energy balance, determining how much solar energy is absorbed, reflected, or transmitted through different atmospheric layers. Water vapor represents the most important greenhouse gas, trapping outgoing long-wave radiation and maintaining Earth's surface temperatures at levels suitable for liquid water. Latent heat release represents one of the atmosphere's most powerful energy sources, occurring whenever water vapor condenses into liquid or ice. This process powers thunderstorms, hurricanes, and other convective phenomena, converting the invisible energy stored in water vapor into the kinetic energy of wind and the potential energy of atmospheric motion. Atmospheric windows allow specific wavelengths of radiation to pass through the atmosphere with minimal absorption, creating spectral bands where Earth's surface can radiate energy directly to space. These windows are crucial for Earth's energy balance, providing pathways for heat to escape the atmospheric system. Scattering processes determine the colors we see in the sky, from the deep blue of midday to the reds and oranges of sunrise and sunset. Rayleigh, scattering preferentially, affects shorter wavelengths, making the sky appear blue during the day while longer optical paths during sunrise and sunset allow red wavelengths to dominate. Mi scattering occurs when light interacts with particles similar in size to the wavelength of light, creating the white appearance of clouds and the hazy conditions associated with dust and pollution. This type of scattering can create spectacular optical effects when combined with specific particle sizes and atmospheric conditions. Refraction bends light rays as they pass through atmospheric layers of different densities, creating mirages, the green flash phenomenon, and the apparent flattening of the sun's disk as it approaches the horizon. These optical effects demonstrate how the atmosphere acts as a vast, constantly changing lens that distorts our view of distant objects. Atmospheric optics encompasses a vast array of phenomena that transforms simple sunlight into spectacular displays. Coronas appear as coloured rings around the sun or moon when light is diffracted by small, uniform water droplets in thin clouds. These delicate displays require droplets of very specific sizes to create the characteristic alternating bands of colour. Iridescence in clouds occurs when light is diffracted by water droplets or ice crystals, creating patches of brilliant colour that seem to shift and shimmer as the observer moves. These displays are most common in thin clouds near the sun, where uniform droplet sizes create the conditions necessary for strong diffraction effects. Glory phenomena appear as coloured rings centred on the antisolar point, most commonly seen from aircraft looking down at cloud layers below. These displays occur when light is backscattered by water droplets in a complex process that creates circular rainbow patterns centered on the observer's shadow. Atmospheric stability controls the atmosphere's tendency to suppress or enhance vertical motion. Stable conditions inhibit convection, creating those clear, calm days when the air seems to hang motionless and visibility can extend for extraordinary distances. Unstable conditions promote vertical mixing, leading to turbulence, cloud development, and active weather. Conditional instability represents an intermediate state where the atmosphere becomes unstable only if air is lifted to sufficient heights. This type of instability is responsible for triggering afternoon thunderstorms when surface heating provides the initial lift necessary to release the atmosphere's stored instability. Convective inhibition occurs when stable layers in the atmosphere suppress convective development despite the presence of instability aloft. These atmospheric caps can prevent thunderstorm formation for extended periods. But when they're finally breached, the released energy can create particularly intense convective activity. Atmospheric mixing processes operate continuously at scales ranging from molecular diffusion to large-scale turbulent eddies. Turbulent mixing is most efficient at transporting heat, moisture, and momentum through the atmosphere, creating the well-mixed conditions that characterize the daytime boundary layer. Molecular diffusion operates at the smallest scales of atmospheric motion, gradually evening out concentration gradients through random molecular motion. Though slow compared to turbulent mixing, molecular processes become important in the very stable conditions that sometimes develop during clear, calm nights. Atmospheric dispersion determines how pollutants, moisture, and heat spread through the air, affecting everything from air quality to local climate conditions. Strong mixing promotes rapid dispersion, while stable conditions can concentrate materials in narrow layers or specific geographic areas. Ventilation processes control how efficiently the atmosphere can flush out accumulated pollutants or excess heat. Good ventilation requires both horizontal winds to transport materials away from source areas and vertical mixing to disperse them through a deep atmospheric layer. Wind shear represents changes in wind speed or direction over relatively short distances, creating some of the most important conditions for both aviation safety and weather development. Strong wind shear can tear apart developing thunderstorms, but moderate shear can enhance storm organization and longevity. Directional shear occurs when wind direction changes significantly with altitude, while speed shear involves changes in wind velocity. Both types can create rotating motion in the atmosphere, providing the spin necessary for tornado development or the organization of larger-scale storm systems. Low-level wind shear presents particular hazards for aircraft during takeoff and landing, as sudden changes in wind can dramatically affect lift and control. Meteorologists use sophisticated detection systems to identify these invisible hazards and warn pilots of potentially dangerous conditions. Atmospheric momentum represents the motion energy stored in moving air masses, and this momentum can be transferred between different atmospheric layers through various processes. Momentum transport helps explain why surface winds often change when upper-level wind patterns shift, demonstrating the three-dimensional connectivity of atmospheric motion. Geostrophic balance describes the equilibrium between pressure gradient forces and the Coriolis effect that creates the large-scale wind patterns shown on weather maps. This balance explains why winds tend to flow parallel to lines of equal pressure rather than directly from high to low pressure areas. Geostrophic motion occurs when forces other than pressure gradients and Coriolis effects become important, creating departures from the balanced flow patterns. These imbalances drive much of the weather we experience, as they create the convergence and divergence patterns that trigger storm development and dissipation. Atmospheric vorticity measures the rotation tendency of air parcels, providing insights into the development and movement of weather systems. Areas of positive vorticity often coincide with storm development, while negative vorticity tends to suppress weather activity. Potential temperature represents what the temperature of an air parcel would be if it were moved to a standard pressure level, providing a measure of atmospheric stability that remains constant when air moves vertically without exchanging heat with its surroundings. This concept helps meteorologists track air masses and identify atmospheric boundaries. Equivalent potential temperature includes the effects of moisture content, providing an even more comprehensive measure of air mass characteristics. Air masses with similar equivalent potential temperatures tend to have similar weather-producing capabilities, regardless of their current temperature and pressure. Atmospheric energetics involves the various forms of energy present in the atmosphere and how they transform from one type to another. Kinetic energy manifests as wind motion, potential energy exists due to altitude differences, and latent energy is stored in water vapor, awaiting release through condensation processes. Available potential energy represents the maximum amount of kinetic energy that could be generated if all temperature differences in the atmosphere were eliminated through adiabatic motion. This energy reservoir helps explain why some weather patterns can persist and intensify while others quickly dissipate. Convective available potential energy measures the maximum speed that rising air parcels could theoretically achieve if all atmospheric instability were converted to upward motion. High values of this energy indicate conditions favorable for explosive thunderstorm development and severe weather. Helicity combines wind shear and atmospheric vorticity into a single parameter that indicates the potential for rotating thunderstorms and tornado development. High helicity values don't guarantee severe weather, but they identify atmospheric environments where rotating storms are most likely to develop. Storm relative motion describes how thunderstorms move relative to their environmental flow, helping meteorologists predict storm paths and intensity changes. Storms that move slowly relative to their environment often produce the heaviest rainfall and most persistent severe weather. Atmospheric rivers of moisture transport vast quantities of water vapor in narrow bands that can extend for thousands of kilometers. These invisible highways in the sky can carry water equivalent to multiple times the flow of major rivers, demonstrating the atmosphere's remarkable capacity for long-distance moisture transport. Precipitable water measures the total amount of water vapor in a vertical column of atmosphere, indicating the maximum possible rainfall if all atmospheric moisture could be wrung out simultaneously. High precipitable water values indicate conditions favorable for heavy precipitation when lifting mechanisms are present. Moisture flux represents the transport of water vapor by atmospheric motion, combining wind patterns with humidity levels to show where moisture is being carried through the atmosphere. Understanding moisture flux helps meteorologists predict where precipitation is most likely to develop. Relative humidity describes how close the air is to saturation with water vapor, expressed as a percentage of the maximum moisture the air could hold at its current temperature. Though familiar to most people, relative humidity can be misleading because warm air can hold much more moisture than cold air. Absolute humidity measures the actual amount of water vapor present in air, regardless of temperature. This measure provides a more direct indication of atmospheric moisture content, but is less intuitive than relative humidity for understanding human comfort and weather processes. Dew point temperature represents the temperature at which air would become saturated if cooled at constant pressure and moisture content. This measure provides an absolute indication of atmospheric moisture content and helps predict fog formation, comfort levels, and precipitation potential. Atmospheric pressure systems create the large-scale patterns that dominate weather maps and drive most of the weather changes we experience. High-pressure areas generally bring fair weather and light winds, while low-pressure systems are associated with clouds, precipitation, and more active weather conditions. Pressure gradient force drives atmospheric motion by accelerating air from high pressure toward low pressure areas. The strength of this force depends on how rapidly pressure changes over distance, with steep pressure gradients creating strong winds and gentle gradients producing light air movement. Cyclonic circulation develops around low-pressure centers in the northern hemisphere, creating the counterclockwise rotation patterns visible on satellite images of storm systems. This rotation results from the balance between pressure gradient forces trying to drive air toward the low-pressure center, and Coriolis effects deflecting the motion. Anticyclonic circulation occurs around high-pressure centers, producing clockwise rotation in the northern hemisphere. These circulation patterns typically bring stable weather conditions, clear skies, and light winds, though they can also trap pollutants and create persistent weather patterns. Atmospheric blocking occurs when persistent high-pressure systems disrupt normal weather patterns, redirecting storm tracks and creating prolonged periods of unusual weather. These blocks can cause extended heat waves, droughts, or cold spells by preventing the normal progression of weather systems. Cut-off low-pressure systems become isolated from the main atmospheric flow, creating slow-moving or stationary weather patterns that can persist for days or weeks. These systems often produce prolonged periods of unsettled weather and can be particularly difficult to forecast accurately. Thermal low-pressure systems develop over heated land surfaces, particularly common in arid regions during summer months. These systems typically produce light winds and clear skies, but can enhance thunderstorm development when moisture is available and lifting mechanisms are present. Lee cyclogenesis describes the formation of low-pressure systems on the downwind side of mountain ranges, where complex interactions between topography and atmospheric flow create favorable conditions for storm development. The Rocky Mountains and other major mountain ranges regularly spawn these terrain-induced weather systems. As the gentle currents of our atmospheric journey begin to slow, we find ourselves suspended between understanding and wonder, like particles of moisture drifting through the evening air. The atmosphere continues its eternal dance around us, mixing and swirling, heating and cooling, creating and destroying the endless patterns that make each day's weather a unique expression of physical forces too vast and intricate for any single mind to fully comprehend. In these quiet moments, as your breathing deepens and your thoughts begin to soften like morning mist, remember that you are part of this magnificent atmospheric system. Every breath you take participates in the global circulation of gases that connects you to distant places and times. The oxygen entering your lungs may have been released by a forest thousands of miles away, while the carbon dioxide you exhale will eventually nourish plants you'll never see. The temperature of your skin adjusts constantly to the thermal conditions around you, making you a tiny part of the vast heat exchange system that drives weather patterns across the globe. Your body's moisture contributes to the humidity of your immediate environment, while the warmth you generate becomes part of the complex energy budget that influences local atmospheric conditions. Tonight, as you rest within this invisible ocean of air, consider how atmospheric rivers weave their silent stories across continents. These narrow corridors of moisture, invisible to the naked eye yet carrying the water equivalent of 15 Amazon rivers, demonstrate the atmosphere's remarkable ability to connect distant shores. When these ethereal highways encounter mountain ranges, they release their liquid cargo in gentle rains or dramatic deluges, nourishing ecosystems thousands of kilometers from their oceanic origins. The atmosphere remembers through mechanisms more subtle than human memory, yet far more persistent. Soil moisture creates one form of this atmospheric recollection, where dry earth promotes continued drought, while saturated ground helps maintain humid conditions for weeks or months. This feedback whispers across landscapes, creating self-reinforcing patterns that can persist long after the original weather event has passed. Snow cover provides another chapter in the atmosphere's memory book, reflecting incoming solar radiation with such efficiency that winter's white blanket can influence weather patterns well into spring. The brilliant albedo of fresh snow bounces 90% of sunlight back to space, maintaining cool surface temperatures that affect everything from local precipitation patterns to the timing of seasonal transitions. Ocean temperatures offer the atmosphere its longest and most stable memories. The enormous heat capacity of water bodies allows them to store and slowly release thermal energy across seasons and years, moderating coastal climates and influencing weather patterns across entire ocean basins. These aquatic thermal banks help explain why island nations experience such remarkably stable climates compared to continental interiors. Boundary layers develop their own daily rhythms, expanding and contracting like the slow breathing of the atmosphere itself. During stable nighttime hours, this lowest atmospheric layer can shrink to mere dozens of meters thick, creating a shallow realm where sounds travel with crystalline clarity, and pollutants become concentrated in narrow bands close to the Earth. As daylight returns and solar heating begins its work, convective boundary layers grow to heights of several kilometers, creating well-mixed atmospheric zones where thermal updrafts carry moisture, heat, and even living creatures to impressive altitudes. These invisible elevators of air allow soaring birds to travel vast distances without a single wing beat, riding the atmosphere's own vertical currents with elegant efficiency. Entrainment processes occur at the boundary between the mixed layer below and the free atmosphere above, where turbulent eddies gradually incorporate air from aloft. This slow mixing can dramatically alter the character of surface air, as dry air from above mingles with humid surface conditions, or as stable air from higher altitudes dampens convective activity below. Atmospheric waves propagate through the air with the same fluid grace as ocean swells, carrying energy across vast distances without transporting the air itself. These invisible undulations can be generated by mountain ranges, thunderstorm complexes, or even seismic events, creating disturbances that travel through the atmosphere at speeds approaching that of sound. Internal gravity waves represent some of the atmosphere's most elegant oscillations, occurring when stable air is displaced vertically and then bobs up and down under the restoring force of buoyancy. These waves can propagate horizontally for thousands of kilometers, carrying energy from storm systems or mountain interactions to distant locations where they might trigger cloud formation or clear existing cloud decks through their gentle vertical motions. Atmospheric tides, though far more subtle than their oceanic counterparts, create measurable pressure variations that follow the sun's daily heating cycle with remarkable precision. These atmospheric rhythms are most pronounced in tropical regions, where the regular pulse of solar heating creates pressure waves that circle the globe like clockwork. demonstrating the atmosphere's sensitivity to even subtle energy inputs. Pressure waves allow atmospheric disturbances to communicate across incredible distances, traveling at speeds that can circle the Earth multiple times. Major volcanic eruptions create these atmospheric messages that sensitive instruments can detect as they race around the planet, carrying information about distant catastrophic events to recording stations thousands of kilometers away. Temperature oscillations in the atmosphere operate across timescales that span from the familiar daily cycles to mysterious, multi-decadal rhythms that influence climate patterns across entire generations. While daily temperature swings are easily observed, the atmosphere also exhibits weekly, monthly, seasonal, and even century-long temperature cycles that affect everything from agricultural productivity to ice sheet stability. Radiative processes control the delicate energy balance that maintains Earth's habitability, determining precisely how much solar energy becomes absorbed, reflected, or transmitted through different atmospheric layers. Water vapor serves as the atmosphere's most important greenhouse gas, creating an invisible blanket that traps outgoing heat and maintains surface temperatures suitable for liquid water and life as we know it. Latent heat release represents one of the most powerful energy sources available to atmospheric processes, occurring whenever water vapor undergoes the phase transition to liquid or ice. This invisible energy conversion powers the towering cumulonimbus clouds of thunderstorms, the spiraling winds of hurricanes, and the gentle upward motion that creates fair weather cumulus formations. Atmospheric windows allow specific wavelengths of electromagnetic radiation to pass through the air with minimal interference, creating spectral pathways where Earth's surface can radiate excess energy directly to space. These invisible corridors are crucial for maintaining planetary energy balance, providing escape routes for heat that would otherwise accumulate in the atmospheric system. Scattering processes paint the sky in the colors we associate with different times of day and weather conditions. Rayleigh scattering preferentially affects shorter blue wavelengths during midday hours, while the longer atmospheric paths of sunrise and sunset allow red and orange wavelengths to dominate our visual experience of these transition periods. Me scattering occurs when light encounters particles similar in size to its own wavelength, creating the brilliant white appearance of clouds and the hazy conditions associated with dust storms and urban pollution. This type of light interaction can produce spectacular optical displays when atmospheric conditions align to create uniform particle distributions at specific altitudes. Refraction gently bends light rays as they pass through atmospheric layers of varying density, creating the shimmering mirages we see on hot pavement, the mysterious green flash phenomenon at sunset, and the apparent flattening of celestial objects as they approach the horizon. These optical effects reveal how the atmosphere acts as an enormous, constantly shifting lens that subtly alters our perception of the world beyond. Atmospheric optics encompasses a treasury of phenomena that transform ordinary sunlight into extraordinary displays. Coronas appear as delicate colored rings around the sun or moon when light undergoes diffraction through thin clouds containing water droplets of remarkably uniform size. These ethereal displays require such precise conditions that they appear almost magical when they grace the sky. Iridescence in clouds creates patches of brilliant, shifting color that seem to dance and shimmer as observers change their viewing angle. These displays occur when light waves interact with water droplets or ice crystals through complex diffraction processes, creating localized areas where clouds appear to glow with rainbow hues. Glory phenomena manifest as colored rings centered on the antisolar point, most commonly visible from aircraft looking down through cloud layers below. These circular rainbow patterns occur when light undergoes a complex backscattering process that creates colored rings centered precisely on the observer's shadow, a phenomenon that requires very specific droplet sizes and viewing geometry. Atmospheric stability governs the atmosphere's fundamental tendency to either suppress or enhance vertical motion. Stable atmospheric conditions create those remarkably clear, calm days when air seems to hang motionless and distant objects appear with startling clarity. Unstable conditions promote vigorous vertical mixing, leading to turbulence, rapid cloud development, and active weather systems. Conditional instability represents an atmospheric state poised between stability and chaos, where the air becomes unstable only if lifted to sufficient heights. This delicate balance is responsible for triggering many afternoon thunderstorms, where surface heating provides just enough initial lift to release the atmosphere's stored potential for convective activity. Convective inhibition occurs when stable atmospheric layers act like invisible caps, suppressing thunderstorm development despite the presence of significant instability at higher levels. These atmospheric barriers can prevent storm formation for hours or days, but when they finally weaken or break, the released energy often creates particularly intense and long-lasting convective systems. Atmospheric mixing operates continuously across scales ranging from molecular diffusion to massive turbulent eddies spanning kilometers. Turbulent mixing proves most efficient at transporting heat, moisture, and atmospheric constituents, creating the well-mixed conditions that characterize active daytime boundary layers and convective environments. Molecular diffusion works at the smallest scales of atmospheric motion, gradually evening out concentration differences through random molecular movement. Though slow compared to turbulent processes, molecular mixing becomes critically important during very stable atmospheric conditions, particularly during clear, calm nighttime periods when turbulence nearly ceases. Atmospheric dispersion determines how efficiently pollutants, water vapor, and thermal energy spread through the air, affecting local air quality, humidity patterns, and temperature distributions. Strong atmospheric mixing promotes rapid dispersion and dilution, while stable conditions can concentrate materials in narrow layers or specific geographic regions. Ventilation processes control the atmosphere's ability to flush accumulated materials and excess energy from local areas. Effective atmospheric ventilation requires both horizontal winds to transport materials away from source regions and vertical mixing to distribute them through deep atmospheric layers, preventing dangerous accumulations near the surface. Wind shear creates some of the most significant conditions for both weather development and aviation safety, representing changes in wind speed or direction across relatively short distances. While strong wind shear can disrupt and weaken developing storm systems, moderate shear often enhances storm organization and can contribute to the development of rotating weather systems. Directional shear involves changes in wind direction with altitude, while speed shear relates to variations in wind velocity. Both types can impart rotation to atmospheric motion, providing the spinning motion necessary for tornado development or the organization of larger mesocyclone systems within supercell thunderstorms. Low-level wind shear presents invisible hazards for aircraft during the critical phases of takeoff and landing, as sudden changes in wind conditions can dramatically affect aircraft performance. Sophisticated detection systems now monitor airports for these dangerous wind patterns, providing early warning of conditions that could threaten aviation safety. Atmospheric momentum represents the motion energy stored within moving air masses, and this momentum can transfer between different atmospheric levels through various mechanical processes. Understanding momentum transport helps explain why surface wind patterns often respond to changes in upper-level atmospheric flow, demonstrating the three-dimensional connectivity of atmospheric circulation. Geostrophic balance describes the elegant equilibrium between pressure gradient forces and Coriolis effects that creates the large-scale wind patterns depicted on weather maps. This balance explains why winds typically flow parallel to pressure contours, rather than directly from high toward low-pressure areas, creating the graceful curved flow patterns visible in satellite imagery. Agiost effects become important. Creating departures from rothic motion occurs when forces beyond pressure gradients and Coriolis balanced flow that drive much of our observable weather. These imbalances generate the convergence and divergence patterns that trigger storm development, intensification, and eventual dissipation. Atmospheric vorticity measures the rotation tendency inherent in air parcels, providing crucial insights into weather system development and movement. Regions of positive vorticity often coincide with areas favorable for storm development, while negative vorticity tends to suppress convective activity and promote stable atmospheric conditions. Potential temperature represents what an air parcel's temperature would become if moved to a standard pressure level without exchanging heat with surrounding air. This concept provides meteorologists with a stability measure that remains constant during vertical motion, helping to identify atmospheric boundaries and track air mass movements. Equivalent potential temperature incorporates moisture effects into potential temperature calculations, offering an even more comprehensive characterization of air mass properties. Air masses sharing similar equivalent potential temperatures tend to exhibit comparable weather-producing capabilities, regardless of their current temperature and pressure values. Atmospheric energetics encompasses the various energy forms present in the atmosphere and their continuous transformations. Kinetic energy manifests as wind motion. Potential energy exists due to gravitational effects on air at different altitudes, and latent energy remains stored in water vapor, awaiting release through condensation processes. Available potential energy quantifies the maximum kinetic energy that could theoretically be generated if all atmospheric temperature differences were eliminated through adiabatic motion. This energy reservoir helps explain why certain weather patterns can persist and intensify, while others quickly dissipate into calmer conditions. Convective available potential energy measures the maximum speed that rising air parcels could achieve if all atmospheric instability converted to upward motion. High values indicate atmospheric environments primed for explosive thunderstorm development and potentially severe weather conditions. Helicity combines wind shear and atmospheric vorticity into a single parameter indicating potential for rotating thunderstorms and tornado development. While high helicity values don't guarantee severe weather occurrence, they identify atmospheric environments where supercells and tornadoes are statistically most likely to form. Storm relative motion describes how weather systems move compared to their environmental atmospheric flow, helping forecasters predict storm paths and intensity changes. Storms moving slowly relative to environmental winds often produce the heaviest precipitation and most persistent, severe weather impacts. Atmospheric moisture transport occurs through invisible rivers of water vapor that can extend thousands of kilometers, while carrying moisture equivalent to multiple major terrestrial rivers. These atmospheric highways demonstrate the remarkable capacity for long-distance water transport through air currents, connecting distant oceanic and continental water sources. Precipitable water quantifies the total atmospheric water vapor in a vertical air column, indicating theoretical maximum precipitation if all moisture could somehow be extracted simultaneously. High precipitable water values suggest favorable conditions for heavy rainfall when appropriate lifting mechanisms become available. Moisture flux combines wind patterns with atmospheric humidity to reveal where water vapor is being transported through the atmosphere. Understanding these moisture streams helps meteorologists predict precipitation development and intensity, particularly when combined with knowledge of lifting mechanisms and atmospheric stability. Relative humidity describes atmospheric moisture content as a percentage of maximum possible water vapor at current temperature conditions. Though familiar to most people, relative humidity can be misleading because warm air can hold exponentially more moisture than cold air at the same relative humidity percentage. Absolute humidity measures actual water vapor quantity present in air regardless of temperature variations. This measurement provides more direct indication of atmospheric moisture content, but proves less intuitive than relative humidity for understanding human comfort levels and basic weather processes. Dew point temperature represents the temperature at which air would become saturated if cooled at constant pressure and moisture content. This measure provides absolute indication of atmospheric moisture content and helps predict fog formation potential, human comfort levels, and precipitation development. Atmospheric pressure systems create the large-scale circulation patterns that dominate weather maps and drive most observable weather changes. High-pressure areas typically bring fair weather and light wind conditions, while low-pressure systems associate with cloud development, precipitation, and more dynamic atmospheric activity. Pressure gradient force drives atmospheric motion by accelerating air from high toward low pressure regions. The strength of this driving force depends on how rapidly pressure changes across distance, with steep pressure gradients generating strong winds and gentle gradients producing light air movement. Cyclonic circulation develops around low pressure centers, creating the counterclockwise rotation patterns visible in Northern Hemisphere satellite imagery of storm systems. This rotation results from balance between pressure gradient forces driving air toward the low center and Coriolis effects deflecting the inward flowing motion. Anticyclonic circulation occurs around high pressure centers, producing clockwise rotation in Northern Hemisphere systems. These circulation patterns typically bring stable weather conditions, clear skies and light winds, though they can also trap air pollutants and create persistent atmospheric stagnation. Atmospheric blocking develops when persistent high-pressure systems disrupt normal weather flow patterns, redirecting storm tracks and creating prolonged periods of unusual weather conditions. These blocks can cause extended heat waves, drought conditions, or cold spells by preventing normal weather system progression. Cut-off low-pressure systems become isolated from main atmospheric flow patterns, creating slow-moving or stationary weather features that can persist for days or weeks. These systems often produce extended periods of unsettled weather and present particular challenges for accurate weather forecasting. Thermal low-pressure systems develop over intensely heated land surfaces, particularly common in arid regions during summer months. These heat-induced circulation patterns typically produce light winds and clear skies, but can enhance thunderstorm development when adequate moisture and lifting mechanisms become available. Lee cyclogenesis describes low-pressure system formation on the downwind side of mountain ranges, where complex interactions between topography and atmospheric flow create favorable conditions for storm development. Major mountain ranges regularly spawn these terrain-induced weather systems that can intensify into significant storm complexes. Upper-level divergence creates favorable conditions for surface low-pressure development by removing air mass from upper atmospheric levels, allowing surface air to rise and pressure to decrease. This process demonstrates the critical three-dimensional connections between upper and lower atmospheric levels in weather system development. Surface convergence occurs when horizontal air flows meet and are forced upward, creating lifting that can trigger cloud formation and precipitation development. These convergence zones often mark boundaries between different air masses or result from terrain effects that channel atmospheric flow into collision zones. Warm air advection involves horizontal transport of higher temperature air masses, typically associated with rising motion and weather system development. This process often precedes the arrival of storm systems and can create the atmospheric destabilization necessary for thunderstorm formation. Cold air advection represents horizontal transport of lower temperature air masses, usually associated with sinking motion and weather clearing. However, when cold air moves over warmer surfaces, it can become unstable and produce lake effect snow, sea effect precipitation, or other convective phenomena. Differential heating creates temperature contrasts that drive atmospheric circulation patterns at scales ranging from local sea breezes to global trade wind systems. These thermal differences provide the energy source for most atmospheric motion, converting solar heating variations into kinetic energy of moving air. Adiabatic processes involve temperature changes that occur when air parcels expand or compress without exchanging heat with their surroundings. Rising air cools adiabatically while sinking air warms, creating the temperature structure that determines atmospheric stability and cloud formation potential. Diabatic processes involve heat exchange between air parcels and their surroundings through radiation, conduction, or latent heat release. These processes can modify air mass characteristics and create the temperature changes that drive weather development and atmospheric circulation patterns. Atmospheric soundings provide vertical profiles of temperature, humidity, and wind conditions that reveal the three-dimensional structure of atmospheric conditions. These balloon-borne measurements offer crucial insights into atmospheric stability, wind shear, and moisture distribution that surface observations cannot provide. Radio sonde observations carry sophisticated instruments high into the atmosphere, transmitting real-time data about conditions from surface levels to stratospheric altitudes. These twice-daily launches from weather stations worldwide provide the vertical atmospheric information essential for weather prediction and atmospheric research. Upper air analysis examines atmospheric conditions at various levels throughout the troposphere and lower stratosphere, revealing the three-dimensional structure of weather patterns. This analysis helps meteorologists understand the driving mechanisms behind surface weather development and movement. Atmospheric profiling uses various remote sensing techniques to examine vertical atmospheric structure without requiring balloon-borne instruments. Ground-based radar, satellite observations, and acoustic systems can provide continuous monitoring of atmospheric conditions at multiple levels. Nowcasting represents short-term weather prediction, focusing on conditions over the next few hours, using current observations and rapidly updating numerical models. This approach proves particularly valuable for aviation, emergency management, and outdoor activities where immediate weather conditions matter most. Ensemble forecasting runs multiple weather prediction models or multiple versions of the same model to assess forecast uncertainty and provide probability-based predictions. This approach acknowledges the inherent limitations of atmospheric predictability while providing more useful information about forecast confidence. Numerical weather prediction employs complex mathematical models that solve atmospheric physics equations to predict future weather conditions. These models require enormous computational resources and represent some of the most sophisticated applications of mathematical modeling to real-world problems. As we drift deeper into this atmospheric meditation, the invisible world around us continues its eternal circulation. Water molecules that may have fallen as snow on distant mountain peaks could now be rising as vapor from tropical seas. Dust particles lifted from African deserts dance through upper-level winds toward Amazon rainforests they will eventually nourish. The atmosphere connects all places and all times through its ceaseless motion, creating a global circulation system that knows no borders, recognizes no boundaries, and operates according to physical laws older than continents. Your breath mingles with this vast atmospheric ocean, each inhalation drawing in molecules that have traveled impossible distances, each exhalation contributing to the endless circulation that sustains all life on Earth. The oxygen entering your lungs may have been released by phytoplankton in distant oceans or by forests on continents you've never seen. The carbon dioxide you release will nourish plants growing in places you'll never visit, becoming part of their structure, their growth, their contribution to the atmospheric cycle that continues without pause. In the gentle rhythm of your breathing, you participate in atmospheric processes that operate on timescales from microseconds to millennia. The air around you carries information about weather systems thousands of kilometers away. Pressure changes that originated in different hemispheres, and chemical signatures that tell stories of volcanic eruptions, ocean evaporation, and forest photosynthesis. Even as you rest, temperature differences drive circulation patterns that will determine tomorrow's weather. Somewhere, thermal updrafts are carrying moisture toward condensation levels where tomorrow's clouds will form. Somewhere else, radiational cooling is creating temperature inversions that will trap fog in valleys, until morning sun provides enough energy to mix the atmosphere and clear the air. The atmosphere holds the memory of every storm that has passed, every temperature extreme that has occurred, every interaction between air and land and sea. This invisible archive surrounds you as you sleep, whispering stories of atmospheric events that shaped climates, influenced civilizations, and continue to determine the conditions that make Earth habitable. Tonight, as atmospheric rivers flow silently overhead and pressure systems slowly migrate across continents, the same physical processes that create gentle morning dew also power the mightiest hurricanes. The same molecular motions that allow you to detect the fragrance of distant flowers also transport pollutants, pollen, and the chemical signatures of ecosystems across vast distances. Jet streams race through the darkness above, steering weather systems along their meandering paths while you rest beneath their influence. These rivers of air, invisible yet immensely powerful, connect your local weather to atmospheric events occurring thousands of kilometers away, demonstrating the truly global nature of atmospheric circulation. Boundary layers are settling into their nighttime configurations around the world, becoming stable and stratified as radiational cooling creates those calm, still conditions that allow dew formation and frost development. In other places where the sun still shines, convective boundary layers are mixing air through great depths, creating the turbulent conditions that generate afternoon thunderstorms and fair weather cumulus clouds. The atmosphere's memory operates through soil moisture that will influence next week's weather, through snow cover that will affect regional temperatures for months, through ocean thermal patterns that will influence seasons yet to come. These forms of atmospheric memory demonstrate how today's weather conditions participate in creating the climate conditions of tomorrow, next year, and years beyond. As your thoughts become as light and drifting as morning mist, remember that you are suspended within an atmospheric system of incredible complexity and remarkable beauty. Every weather phenomenon, from the gentlest breeze to the most dramatic thunderstorm, results from the same fundamental processes of heating, cooling, rising, sinking, and flowing that operate according to physical laws as reliable as gravity itself. The atmosphere continues its work while you sleep, redistributing heat from warm regions to cold ones, transporting moisture from oceans to continents, creating the pressure patterns that will determine tomorrow's wind direction and speed. This invisible machinery operates with efficiency that surpasses any human engineering, powered entirely by solar energy and organized by the Earth's rotation into patterns of breathtaking elegance and complexity. In this quiet moment, between waking and sleeping, you are part of something infinitely larger than yourself, yet as intimate as your next breath. The atmosphere that surrounds you extends from the ground beneath your feet to the edge of space itself, creating a protective envelope that makes all life possible, while generating the endless variety of weather that makes each day unique and unpredictable. In this vast atmospheric embrace that cradles our planet, pressure waves travel through the air like whispers carrying messages across impossible distances. These invisible messengers move at speeds approaching that of sound itself, circling the globe multiple times and carrying information about distant volcanic eruptions, major storms, and seismic events to sensitive instruments thousands of kilometers away from their origins. The atmosphere remembers these disturbances, echoing them around the world in patterns too subtle for human senses, but clearly detectable to those who know how to listen. Temperature oscillations pulse through the atmosphere on timescales that span from the familiar rhythm of day and night to mysterious cycles that last decades or even centuries. While we easily notice daily temperature swings, the atmosphere also breathes with weekly, monthly, and seasonal rhythms that influence everything from agricultural growing seasons to the migration patterns of birds and the flowering times of plants. These longer cycles connect weather patterns across years and generations, creating climate signatures that persist far longer than any individual storm or heatwave. Radiative processes control the delicate energy balance that keeps our planet habitable, determining precisely how much solar energy becomes absorbed by surfaces, reflected back to space, or trapped by atmospheric gases. Water vapor acts as the atmosphere's most important invisible blanket, creating a greenhouse effect that maintains surface temperatures warm enough for liquid water to exist. Without this natural thermal regulation, Earth would be a frozen world where life as we know it could never have emerged. Latent heat release represents one of the most powerful energy sources available to atmospheric systems, occurring whenever water vapor undergoes its transformation into liquid droplets or ice crystals. This process powers the towering thunderheads that reach toward the stratosphere, fuels the spiraling winds of tropical cyclones, and drives the gentle convection that creates those puffy fair weather clouds that drift lazily across summer skies. Every time water changes phase in the atmosphere, it releases or absorbs enormous amounts of energy that become available to drive atmospheric motion. Atmospheric windows allow specific wavelengths of electromagnetic radiation to pass through the air with minimal interference, creating invisible pathways where Earth's surface can release excess heat directly to the vacuum of space. These spectral corridors are essential for maintaining planetary energy balance, providing escape routes for thermal radiation that would otherwise accumulate and overheat the atmospheric system. The transparency of these windows depends on the precise composition of atmospheric gases and can be altered by changes in water vapor, carbon dioxide, or other trace constituents. Scattering processes paint the sky in the familiar colors we associate with different times of day and weather conditions. During midday hours, when the sun rides high, shorter blue wavelengths scatter more readily than longer colors, creating that deep azure dome we call the sky. As the sun approaches the horizon, its light must travel through increasingly thick layers of atmosphere, scattering away the blues and allowing the warm reds and oranges to dominate our visual experience of sunrise and sunset. Me-scattering occurs when light encounters particles roughly similar in size to its own wavelength, creating the brilliant white appearance of clouds and the hazy conditions we associate with dust storms, wildfire smoke, or urban air pollution. When atmospheric conditions align to create uniform particle distributions at specific altitudes, this type of scattering can produce some of nature's most spectacular optical displays, turning ordinary clouds into canvases of shifting light and color. Refraction gently bends light rays as they pass through atmospheric layers of varying density, creating the shimmering mirages that dance above hot pavement on summer days. The mysterious green flash that sometimes appears just as the sun disappears below a clear horizon, and the apparent flattening of celestial objects as they approach the edge of our vision. These optical effects reveal how the atmosphere acts as an enormous, constantly changing lens that subtly modifies our perception of the world around us. Atmospheric optics encompasses a vast collection of phenomena that transform ordinary sunlight into extraordinary displays of natural artistry. Coronas appear as delicate rings of color around the sun or moon when light undergoes diffraction through thin clouds containing water droplets of remarkably uniform size. These ethereal displays require such precise atmospheric conditions that they seem almost magical when they grace the sky, appearing and disappearing as cloud droplet sizes change with atmospheric currents. Iridescence in clouds creates patches of brilliant, shifting color that seem to pulse and shimmer as observers change their position or viewing angle. These displays occur when light waves interact with water droplets or ice crystals through complex diffraction processes, creating localized areas where clouds appear to glow with rainbow hues that shift from blue to green to red as the observer moves or as the cloud particles drift through different orientations. Glory phenomena manifest as colored rings centered on the anti-solar point, that spot in the sky directly opposite the sun from the observer's perspective. These displays are most commonly visible from aircraft looking down through cloud layers below, where they appear as circular rainbow patterns centered precisely on the aircraft's shadow. The phenomenon requires very specific droplet sizes and viewing geometry, making it a relatively rare treat for those fortunate enough to witness it. Atmospheric stability, governs the fundamental tendency of air to either suppress or enhance vertical motion, creating some of the most important conditions for weather development. Stable atmospheric environments produce those remarkably clear, calm days when air seems to hang motionless and distant mountains appear with startling clarity through the crystalline atmosphere. Unstable conditions promote vigorous vertical mixing, leading to turbulence, rapid cloud development, and the dynamic weather systems that bring change and variety to our daily atmospheric experience. Conditional instability represents an atmospheric state balanced precariously between stability and explosive development, where air becomes unstable only if lifted to sufficient heights, where temperature and moisture conditions favor continued upward motion. This delicate atmospheric balance is responsible for triggering many afternoon and evening thunderstorms, where surface heating or other lifting mechanisms provide just enough initial upward push to release the atmosphere's stored potential for dramatic convective activity. Convective inhibition occurs when stable atmospheric layers act like invisible atmospheric lids, suppressing thunderstorm development despite the presence of significant instability at higher levels. These atmospheric barriers can prevent storm formation for hours or even days, building up atmospheric energy like a coiled spring. When these inhibiting layers finally weaken or break down, the released energy often creates particularly intense and long-lasting convective systems that can produce severe weather. Atmospheric mixing operates continuously across scales ranging from the smallest molecular movements to massive turbulent eddies that span many kilometers. Turbulent mixing proves most efficient at transporting heat, moisture, and various atmospheric constituents, creating the well-mixed conditions that characterize active daytime boundary layers and the vigorous environments found within and around thunderstorm systems. Molecular diffusion works at the most fundamental scales of atmospheric motion, gradually evening out concentration differences through the random thermal motion of individual molecules. Though extremely slow compared to turbulent processes, molecular mixing becomes critically important during very stable atmospheric conditions, particularly during those clear, calm nighttime periods when turbulence nearly ceases and the atmosphere settles into layers as distinct as oil floating on water. Atmospheric dispersion determines how efficiently various substances spread through the air, affecting everything from local air quality to the distribution of natural pollen and the transport of moisture from one region to another. Strong atmospheric mixing promotes rapid dispersion and dilution of concentrated materials, while stable conditions can trap substances in narrow layers or confine them to specific geographic areas for extended periods. Ventilation processes control the atmosphere's ability to flush accumulated materials and excess energy from local areas, preventing dangerous buildups of heat, moisture, or airborne substances. Effective atmospheric ventilation requires both horizontal winds strong enough to transport materials away from source regions and sufficient vertical mixing to distribute them through deep atmospheric layers rather than allowing them to accumulate near the surface. Wind shear creates some of the most significant conditions for both weather development and aviation safety, representing changes in wind speed or direction that occur across relatively short distances in space or time. While very strong wind shear can disrupt and weaken developing storm systems by tearing them apart, moderate amounts of shear often enhance storm organization and can contribute to the development of rotating weather systems that produce the most severe atmospheric phenomena. Directional shear involves systematic changes in wind direction with altitude, while speed shear relates to variations in wind velocity at different atmospheric levels. Both types of shear can impart rotation to atmospheric motion, providing the spinning tendency necessary for tornado development within supercell thunderstorms, or the organization of larger mesocyclone systems that can persist for hours and travel hundreds of kilometers. Low-level wind shear presents invisible hazards for aircraft during the critical phases of takeoff and landing, where sudden changes in wind conditions can dramatically affect aircraft performance and control. Sophisticated detection systems now continuously monitor airports and flight paths for these dangerous wind patterns, providing pilots and air traffic controllers with early warnings of atmospheric conditions that could threaten aviation safety. Atmospheric momentum represents the motion energy stored within moving air masses, and this momentum can transfer between different atmospheric levels through various mechanical and thermodynamic processes. Understanding momentum transport helps explain why surface wind patterns often respond to changes in upper-level atmospheric flow, demonstrating the intricate three-dimensional connectivity that links atmospheric motion at all levels, from ground to stratosphere. Geostrophic balance describes the elegant equilibrium between pressure gradient forces trying to accelerate air toward low-pressure areas and Coriolis effects that deflect moving air due to Earth's rotation. This balance explains why winds typically flow parallel to lines of equal pressure rather than directly from high toward low-pressure regions, creating the gracefully curved flow patterns visible in satellite imagery of large-scale weather systems. Ageostrophic motion occurs when forces other than pressure gradients and Coriolis effects become important in determining atmospheric flow, creating departures from balanced conditions that drive much of the weather we actually observe and experience. These imbalances generate the convergence and divergence patterns that trigger storm development, intensification, and eventual dissipation as atmospheric systems evolve through their life cycles. Atmospheric vorticity measures the rotation tendency inherent in air parcels, providing crucial insights into weather system development and the likelihood of storm formation in specific atmospheric environments. Regions of positive vorticity often coincide with areas favorable for storm development and intensification, while negative vorticity tends to suppress convective activity and promote more stable atmospheric conditions. Potential temperature represents what an air parcel's temperature would become if it were moved to a standard pressure level without exchanging heat with the surrounding atmosphere. This concept provides meteorologists with a measure of atmospheric stability that remains constant during dry vertical motion, making it invaluable for identifying atmospheric boundaries, tracking air mass movements, and understanding the thermal structure of the atmosphere. Equivalent potential temperature incorporates the effects of atmospheric moisture into potential temperature calculations, offering an even more comprehensive way to characterize air mass properties and atmospheric stability. Air masses that share similar equivalent potential temperatures tend to exhibit comparable weather-producing capabilities regardless of their current temperature, pressure, and altitude, making this measure particularly useful for forecasting convective potential. Atmospheric energetics encompasses the various forms of energy present in the atmosphere and their continuous transformations from one type to another. Kinetic energy manifests as the motion of wind. Potential energy exists due to gravitational effects on air masses at different altitudes, and latent energy remains stored in water vapor throughout the atmosphere, waiting to be released through the condensation processes that power weather systems. Available potential energy quantifies the maximum amount of kinetic energy that could theoretically be generated if all atmospheric temperature differences were eliminated through adiabatic motion processes. This energy reservoir helps explain why certain weather patterns can persist and intensify over time, while others quickly dissipate into calmer, more uniform atmospheric conditions. Convective available potential energy measures the theoretical maximum speed that rising air parcels could achieve if all atmospheric instability were converted into upward motion through convective processes. High values of this energy parameter indicate atmospheric environments that are primed for explosive thunderstorm development and potentially severe weather conditions, while low values suggest more stable atmospheric conditions. Helicity combines measurements of wind shear and atmospheric vorticity into a single parameter that indicates the potential for rotating thunderstorms and tornado development. While high helicity values don't guarantee that severe weather will occur, they identify atmospheric environments where supercell thunderstorms and tornadoes are statistically most likely to form when other favorable conditions are also present. Storm relative motion describes how weather systems move compared to the environmental atmospheric flow in which they are embedded, helping forecasters predict storm paths, intensity changes, and longevity. Storms that move slowly relative to their environmental winds often produce the heaviest precipitation accumulations and most persistent severe weather impacts, because they remain over the same areas for extended periods. Atmospheric moisture transport occurs through invisible rivers of water vapor that can extend for thousands of kilometers, while carrying moisture quantities equivalent to multiple major terrestrial river systems. These atmospheric highways demonstrate the remarkable capacity for long-distance water transport through air currents, connecting distant oceanic evaporation sources with continental precipitation areas through complex three-dimensional flow patterns. Precipitable water quantifies the total amount of atmospheric water vapor present in a vertical column of air, indicating the theoretical maximum precipitation that could occur if all available moisture could somehow be extracted from the atmosphere simultaneously. High precipitable water values suggest favorable conditions for heavy rainfall when appropriate lifting mechanisms become available to trigger widespread condensation and precipitation processes. Moisture flux combines wind patterns with atmospheric humidity distributions to reveal where and how rapidly water vapor is being transported through different levels of the atmosphere. Understanding these moisture transport patterns helps meteorologists predict where precipitation development is most likely to occur, particularly when combined with knowledge of lifting mechanisms, atmospheric stability, and temperature patterns. Relative humidity describes atmospheric moisture content as a percentage of the maximum possible water vapor that air could hold at its current temperature and pressure conditions. Though familiar to most people through weather reports, relative humidity can be misleading because warm air can hold exponentially more moisture than cold air. So the same relative humidity percentage can represent vastly different absolute moisture amounts. Absolute humidity measures the actual quantity of water vapor present in air regardless of temperature variations or pressure changes. This measurement provides a more direct indication of atmospheric moisture content than relative humidity, but it proves less intuitive than percentage-based measures for understanding human comfort levels and the basic weather processes that most people experience in daily life. Dew point temperature represents the temperature at which air would become completely saturated with water vapor if cooled at constant pressure and moisture content. This measure provides an absolute indication of atmospheric moisture content that doesn't change with temperature fluctuations, making it invaluable for predicting fog formation potential, assessing human comfort levels, and understanding precipitation development processes. Atmospheric pressure systems create the large-scale circulation patterns that dominate weather maps and drive most of the observable weather changes we experience from day to day and season to season. High-pressure areas typically bring fair weather conditions characterized by clear skies, light winds, and stable atmospheric conditions, while low-pressure systems are associated with cloud development, precipitation, and more dynamic atmospheric activity. Pressure gradient force drives atmospheric motion by accelerating air from regions of high pressure toward areas of lower pressure. Much like water flowing downhill under the influence of gravity, the strength of this fundamental driving force depends on how rapidly atmospheric pressure changes across horizontal distances, with steep pressure gradients generating strong winds and gentle gradients producing light, variable air movement. Cyclonic circulation develops around low-pressure centers, creating the characteristic counterclockwise rotation patterns visible in Northern Hemisphere satellite imagery of storm systems, hurricanes, and other weather phenomena. This rotation results from the delicate balance between pressure gradient forces that drive air toward the low-pressure center and Coriolis effects that deflect the inward-flowing motion due to Earth's rotation. Anticyclonic circulation occurs around high-pressure centers, producing clockwise rotation in Northern Hemisphere weather systems. These circulation patterns typically bring stable weather conditions, clear skies, and light winds to affected areas, though they can also trap air pollutants close to the surface and create persistent atmospheric stagnation that affects air quality over large regions. Atmospheric blocking develops when persistent high-pressure systems disrupt the normal flow patterns of weather systems, redirecting storm tracks and creating prolonged periods of unusual weather conditions. These atmospheric roadblocks can cause extended heat waves, persistent drought conditions, or stubborn cold spells by preventing the normal eastward progression of weather systems across continents. Cut-off low-pressure systems become isolated from the main atmospheric flow patterns, creating slow-moving or nearly stationary weather features that can persist for days or even weeks in the same general area. These systems often produce extended periods of unsettled weather conditions and present particular challenges for accurate weather forecasting because they don't follow the typical movement patterns of embedded weather systems. Thermal low-pressure systems develop over intensely heated land surfaces, particularly common in arid desert regions during the hottest months of the year. These heat-induced circulation patterns typically produce light winds and clear skies under normal conditions, but they can enhance thunderstorm development when adequate atmospheric moisture and lifting mechanisms become available to trigger convective processes. Lee cyclogenesis describes the formation of low-pressure systems on the downwind side of major mountain ranges, where complex interactions between topographic features and atmospheric flow patterns create favorable conditions for storm development and intensification. Mountain ranges like the Rockies, Alps, and Andes regularly spawn these terrain-induced weather systems that can evolve into significant storm complexes affecting large geographic areas. Upper-level divergence creates favorable conditions for surface low-pressure development by removing air mass from upper atmospheric levels faster than it can be replaced, allowing surface air to rise and atmospheric pressure to decrease. This process demonstrates the critical three-dimensional connections that exist between upper and lower atmospheric levels in weather system development and intensification. Surface convergence occurs when horizontal air flows meet and are forced to rise, creating the upward motion that can trigger cloud formation, precipitation development, and weather system intensification. These convergence zones often mark the boundaries between different air masses, or result from terrain effects that channel atmospheric flow patterns into collision zones, where vertical motion becomes enhanced. Warm air advection involves the horizontal transport of higher temperature air masses from one region to another, typically associated with rising atmospheric motion and weather system development. This process often precedes the arrival of storm systems and can create the atmospheric destabilization necessary for thunderstorm formation by increasing temperature contrasts and atmospheric instability. Cold air advection represents the horizontal transport of lower temperature air masses, usually associated with sinking atmospheric motion and gradual weather clearing as stable conditions become established. However, when cold air moves over significantly warmer surfaces, like unfrozen lakes, or relatively warm ocean waters, it can become unstable and produce dramatic localized precipitation events. Differential heating creates temperature contrasts that drive atmospheric circulation patterns at scales ranging from local sea breeze systems to global trade wind patterns that encircle the entire planet. These thermal differences provide the fundamental energy source for most atmospheric motion, converting variations in solar heating into the kinetic energy of moving air masses and weather systems. Adiabatic processes involve temperature changes that occur when air parcels expand or compress without exchanging heat with their surrounding environment. Rising air cools adiabatically as it expands in lower pressure conditions, while sinking air warms as it compresses, creating the vertical temperature structure that determines atmospheric stability and the potential for cloud formation. Diabatic processes involve heat exchange between air parcels and their surroundings through radiation, conduction, or the release of latent heat during phase changes of water. These processes can significantly modify air mass characteristics and create the temperature changes that drive weather development and maintain atmospheric circulation patterns over time. Atmospheric soundings provide detailed vertical profiles of temperature, humidity, pressure, and wind conditions that reveal the complete three-dimensional structure of atmospheric conditions from surface levels to the upper troposphere. These measurements offer crucial insights into atmospheric stability, wind shear patterns, and moisture distribution that surface observations alone cannot provide to weather forecasters and researchers. Radiosonde observations involve sophisticated instrument packages carried high into the atmosphere by weather balloons, transmitting real-time data about atmospheric conditions as they ascend through different atmospheric layers. These twice-daily launches from weather stations around the world provide the essential vertical atmospheric information required for weather prediction models and atmospheric research studies. Upper air analysis examines atmospheric conditions at various pressure levels throughout the troposphere and lower stratosphere, revealing the three-dimensional structure of weather patterns and the driving mechanisms behind surface weather development. This analysis helps meteorologists understand how atmospheric disturbances aloft influence surface weather conditions and how weather systems will move and evolve. Atmospheric profiling employs various remote sensing techniques to examine vertical atmospheric structure without requiring balloon-borne instruments, using ground-based radar systems, satellite observations, and acoustic sensors to provide continuous monitoring. These technologies can reveal atmospheric conditions at multiple levels simultaneously, offering high-resolution views of how atmospheric structure changes over time. Nowcasting represents very short-term weather prediction focusing on atmospheric conditions over the next few hours, using current observations and rapidly updating numerical models to provide immediate guidance for critical decisions. This approach proves particularly valuable for aviation operations, emergency management activities, and outdoor events where current and immediate future weather conditions are most important. Ensemble forecasting runs multiple weather prediction models, or multiple versions of the same model, with slightly different initial conditions to assess forecast uncertainty and provide probability-based predictions rather than single deterministic outcomes. This approach acknowledges the inherent limitations of atmospheric predictability while providing more useful information about forecast confidence and the range of possible weather outcomes. Numerical weather prediction employs sophisticated mathematical models that solve complex atmospheric physics equations to simulate future weather conditions based on current atmospheric observations. These models require enormous computational resources and represent some of the most advanced applications of mathematical modeling and supercomputing technology to real-world prediction challenges. As consciousness drifts like morning mist through valleys of sleep, the atmospheric systems around us continue their eternal circulation, operating according to physical principles as reliable and unchanging as the rising and setting of the sun. Somewhere above, jet streams are carving their meandering paths through the upper troposphere, steering weather systems along routes that will determine tomorrow's conditions for millions of people across vast continents. The atmosphere holds conversations in languages we're only beginning to understand. Speaking through pressure oscillations too subtle for human senses, through chemical signatures that tell stories of distant forests and oceans, through temperature patterns that connect today's weather to climate cycles spanning decades and centuries. These atmospheric whispers carry information about volcanic eruptions on the other side of the planet, about the health of rainforests we'll never see, about ice sheets melting in polar regions far from any human habitation. In the gentle rhythm of your slowing breath, you participate in exchanges that connect you to every other breathing organism on Earth. The oxygen molecules entering your lungs may have been released by microscopic phytoplankton in distant oceans, by vast boreal forests, or by the single tree growing outside your window. The carbon dioxide you exhale will nourish plants growing in places you'll never visit, becoming incorporated into their cellular structure, and eventually returning to the atmosphere through decomposition processes that may take years or decades to complete. Boundary layers around the world are settling into their nighttime configurations, becoming stable and stratified as radiational cooling creates those calm, still conditions that allow dew formation on grass blades and frost development on surfaces exposed to the clear night sky. In other parts of the world, where the sun still illuminates the landscape, convective boundary layers are actively mixing air through great depths, creating the turbulent conditions that generate afternoon thunderstorms and fair weather cumulus clouds. The atmosphere's memory operates through mechanisms more subtle than human recollection, yet far more persistent in their effects on future conditions. Soil moisture creates feedback loops that can influence weather patterns for weeks or months, where dry earth promotes continued drought conditions, while saturated ground helps maintain humid atmospheric conditions long after the rains that created them have ended. Ocean temperatures provide the atmosphere with its longest and most stable form of memory, as the enormous heat capacity of water bodies allows them to store and slowly release thermal energy across seasons, years, and even decades. These vast aquatic reservoirs help explain why coastal regions experience such remarkably stable climates compared to continental interiors, and why changes in ocean temperature patterns can influence weather and climate conditions around the entire planet. Snow cover reflects incoming solar radiation with such remarkable efficiency that winter's white blanket can influence regional and even global temperature patterns well into spring and early summer. The brilliant albedo of fresh snow bounces up to 90% of incident sunlight back to space, maintaining cool surface temperatures that affect everything from local precipitation patterns to the timing of seasonal transitions and the behavior of atmospheric circulation systems. Temperature gradients in the atmosphere can be surprisingly sharp, with differences of several degrees occurring across distances of just a few meters or minutes of time. These microscale variations create their own circulation patterns, generating the thermal updrafts that allow soaring birds to travel vast distances without expending energy on wing beats, and the downdrafts that can suddenly affect aircraft performance even in apparently calm atmospheric conditions. Pressure waves propagate through the atmosphere like ripples spreading across a vast pond, carrying information about distant atmospheric disturbances at speeds approaching that of sound itself. These invisible messengers can circle the globe multiple times, creating faint but detectable echoes of major volcanic eruptions, powerful storms, and even large meteors entering Earth's atmosphere from space. Atmospheric electricity extends far beyond the lightning displays we can observe during thunderstorms, encompassing a global electrical circuit that operates continuously between Earth's surface and the ionosphere high above. This planetary electrical system maintains a voltage difference of several 100,000 volts, with thunderstorms around the world acting like batteries that keep the circuit energized and current flowing through the atmosphere even in fair weather areas. The atmosphere's capacity to create optical phenomena rivals the most sophisticated human-made light shows, transforming ordinary sunlight into displays of extraordinary beauty and complexity. From the simple scattering that paints the sky blue during the day and red at sunset, to the complex interactions that create rainbows, halos, and the rare but spectacular fire rainbows that seem to set clouds ablaze with prismatic light. Microscale eddies swirl through the air around us constantly, too small to see but large enough to carry pollen grains, dust particles, and the molecular signatures of distant places. These tiny atmospheric whirlpools operate at the intersection between molecular motion and larger-scale turbulence, creating the mixing processes that distribute heat, moisture, and atmospheric constituents through the lowest layers of the atmosphere. Temperature inversions create fascinating acoustic phenomena that transform the normal behavior of sound waves in the atmosphere, allowing voices to carry across valleys with startling clarity and enabling distant sounds to seem much closer than their actual sources. These atmospheric conditions bend sound waves back toward the ground instead of allowing them to escape upward, creating natural amphitheaters where whispers can be heard clearly at surprising distances. Convective initiation represents one of the atmosphere's most delicate balancing acts, where tiny changes in temperature, moisture, or lifting can determine whether fair weather conditions persist or explosive thunderstorm development begins. The atmosphere often exists in states of conditional instability where it teeters on the edge between stability and dramatic change, waiting for just the right trigger to release enormous amounts of stored energy. Mesoscale circulation patterns operate at intermediate scales between the largest weather systems and individual thunderstorms, creating organized atmospheric motions that can persist for hours and influence weather conditions across areas spanning hundreds of kilometers. These systems include sea breeze circulations that bring relief to coastal areas during hot summer days, mountain valley wind systems that create predictable daily wind patterns in complex terrain, and organized thunderstorm complexes that can produce significant weather impacts. Atmospheric chemistry involves countless simultaneous reactions occurring at different altitudes and under varying temperature, pressure, and radiation conditions. Some of these reactions create the protective ozone layer in the stratosphere that shields Earth's surface from harmful ultraviolet radiation, while others break down pollutants or create new compounds that can affect both atmospheric processes and human health properties and human health. The atmosphere acts as a vast chemical laboratory where sunlight drives photochemical processes. Lightning creates nitrogen compounds that fertilize ecosystems, and natural emissions from plants, oceans, and geological processes interact in complex networks of chemical transformation. Hygroscopic particles demonstrate how microscopic substances can have enormous influences on atmospheric processes, with salt crystals from ocean spray, dust particles from distant deserts, and even bacteria from biological sources serving as nuclei around which water droplets form. These tiny condensation seeds determine whether clouds develop as collections of many small droplets or fewer large ones, affecting everything from precipitation efficiency to the optical properties that determine how much sunlight clouds reflect back to space. Sublimation occurs constantly in winter environments, where snow and ice transform directly into water vapor without first melting into liquid form, creating the gradual disappearance of snow accumulations, even when air temperatures remain below freezing. This elegant phase transition requires energy that comes from solar radiation or ambient heat, demonstrating how the atmosphere continuously exchanges energy and mass through processes that operate below the threshold of casual observation. Atmospheric tides create subtle but measurable pressure variations that follow the sun's daily heating cycle with remarkable regularity, most pronounced in tropical regions where the consistent solar heating creates pressure waves that circle the globe like clockwork. These atmospheric rhythms demonstrate the sensitivity of our fluid atmosphere to even relatively small energy inputs, showing how regular heating patterns create organized responses that can be detected by sensitive instruments around the world. Cloud condensation nuclei exist in an astonishing variety of forms, from sea salt particles that excel at attracting water molecules, to dust grains that provide surfaces for ice crystal formation, to biological particles including pollen, spores, and bacteria that add a living component to atmospheric water cycle processes. The concentration of these microscopic particles can vary by orders of magnitude between pristine oceanic environments and polluted urban areas, dramatically affecting cloud properties and precipitation characteristics. Atmospheric windows in the electromagnetic spectrum allow certain wavelengths of radiation to pass through air with minimal absorption, creating transparency bands that are crucial for Earth's energy balance and for remote sensing applications that monitor weather and climate from space. These spectral doorways enable heat to escape to space, allow satellite instruments to observe atmospheric conditions, and create the wavelength regions where astronomers can observe distant stars and galaxies through our atmosphere. Convective available potential energy accumulates in the atmosphere like stored ammunition for thunderstorms, building up during periods of surface heating and atmospheric moistening until trigger mechanisms release this energy in explosive convective development. The amount of this stored energy helps meteorologists assess the potential severity of thunderstorm activity, with higher values indicating conditions favorable for supercells, tornadoes, and other extreme weather phenomena. Entrainment processes occur at cloud boundaries where turbulent mixing gradually incorporates environmental air into convective updrafts and downdrafts, diluting cloud properties and affecting storm intensity and longevity. This mixing between cloudy and clear air represents one of the most complex aspects of atmospheric physics, involving scales of motion from millimeters to kilometers and timescales from seconds to hours. Kelvin-Helmholtz instability creates waves in the atmosphere that resemble ocean breakers frozen in mid-motion, forming when layers of air move at different speeds and create shearing motions that roll up into distinctive wave patterns. These atmospheric waves sometimes become visible when moisture condenses along the wave crests, creating cloud formations that look remarkably like breaking ocean waves suspended in the sky. Atmospheric gravity waves propagate through stable atmospheric layers, like ripples moving through a three-dimensional fluid, carrying energy from their source regions to distant locations where they can trigger cloud formation, enhance existing weather systems, or create clear air turbulence in apparently calm skies. These waves can travel for thousands of kilometers, demonstrating how atmospheric disturbances in one region can influence weather conditions in areas far removed from the original source. Mountain waves develop when stable air flows over topographic barriers, creating standing wave patterns that extend far downstream from the mountains that generate them. These waves can reach extraordinary altitudes, sometimes extending into the stratosphere, and can create some of the strongest turbulence encountered by aircraft, despite often being completely invisible, except for the occasional lenticular clouds that form in their crests. Boundary layer evolution follows predictable daily cycles that vary with season, weather conditions, surface characteristics, and geographic location. During stable nighttime conditions, this lowest atmospheric layer can shrink to depths of just a few dozen meters, creating shallow zones where pollutants become concentrated and where sound travels with unusual clarity due to the lack of thermal mixing. Thermal circulations develop whenever differential heating creates temperature contrasts between adjacent areas, driving air motion that attempts to eliminate these temperature differences through heat transport. These circulations operate at scales ranging from the gentle heating that creates slope winds in mountainous terrain to the massive temperature contrasts that drive monsoon circulations affecting billions of people across entire continents. Diabatic heating and cooling processes modify air mass characteristics through radiation, conduction, and latent heat release, creating temperature changes that can destabilize atmospheric layers, trigger convective development, or enhance existing weather systems. These processes operate continuously throughout the atmosphere, powered by solar radiation during the day and by radiational cooling to space during night hours. Clear air turbulence occurs in seemingly calm atmospheric conditions, created by wind shear along jet stream boundaries, mountain wave activity, or convective processes that operate below the threshold of cloud formation. This invisible phenomenon can create sudden, severe jolting that affects aircraft flying through apparently tranquil air, demonstrating that significant atmospheric activity can occur without producing any visible indicators. Atmospheric dispersion modeling attempts to predict how pollutants, volcanic ash, radioactive materials, or other substances will spread through the atmosphere under various meteorological conditions. These calculations must account for wind patterns at multiple levels, atmospheric stability, precipitation processes that can remove particles from the air, and chemical transformations that can occur during transport. Convergence zones form where different air masses or wind patterns meet, creating areas of enhanced upward motion that often trigger cloud formation and precipitation development. These zones can be surprisingly persistent, sometimes remaining in nearly the same geographic location for hours or days, creating focused areas of weather activity while adjacent regions remain relatively calm. Low-level jets are ribbons of fast-moving air that form in the lowest few kilometers of the atmosphere, often most pronounced during nighttime hours, when surface cooling creates stable conditions that allow these wind maxima to develop and persist. These jets can transport enormous amounts of moisture from tropical and subtropical regions toward higher latitudes, providing the water vapor that fuels severe thunderstorm development. And so our gentle journey through the invisible ocean of air draws to its quiet close. We've drifted together through 100 peaceful truths about the atmosphere that cradles our world, from the microscopic dance of water molecules to the vast circulation patterns that connect distant continents. Tonight, as you settle into rest, remember that you are forever part of this atmospheric symphony, breathing with the rhythm of a planet that never sleeps. Sweet dreams, and may the gentle currents of air carry you softly toward morning. Air carry you softly toward morning.